All right, cool. Yeah, I'll look forward to it. What do you guys make? Make RSS. Pretty much by far. No song. It's a set factor. I feel like yeah. Yeah, I just want to speak. Oh, yeah. Yeah, that'd be interesting. Are you going to talk mostly about EgoAct stuff?
Using it for sure.
Tons of publications with EgoAct stuff.
Yeah, because they're. What do you're gonna present in the ways?
Yeah, mostly just too.
Are you still doing there? Be like, oh, I'm trying to. I think they're still academic partners. Is that true?
Definitely true.
You're the point person?
Yeah.
Okay.
Yeah. And
It's the outward facing part of
yeah.
area now, so yeah.
And also trying to find a way to make it work in Texas.
Yeah.
Trying to find a way.
That's such
I have a colleague at UT. You might remember. I went around and was like, oh, well, I wrote at UW.
Do the data collection.
Yeah.
So I think they went out of state to collect data for processing.
Yeah.
Doing something.
Child development, and he mentioned need to figure out if about the Illinois citizen, about capturing in Illinois.
Yeah.
Yeah.
So hi, good morning, everyone. So welcome, welcome to EgoAct. On behalf of the organizers, welcome you. I'm Snehal. I'm a PhD candidate at TU Darmstadt with Professor Georgia, who unfortunately couldn't make it today because she's still on maternity leave, but we're all the other organizers are here. Thank you to our sponsor Meta for supporting us with the Best Paper Awards for the workshop. And they also have some cool demonstrations for you today as well, I think. And yeah, if you're like me and this is the first time you're in LA, then yeah, welcome to LA and welcome to USC. We're glad all of you to make it. So, initiating of this workshop was, of course, the big advances we've been making in egocentric perception. The proliferation of VR, AR, and wearable devices that are now ubiquitous and available by everyone, for different companies. And these devices have enabled large-scale egocentric data sets of human activity, of human-object interaction that has really helped us advance this field and really make big gains in, let's say, high-level understanding of humans, the tasks they do, the goals they have, the prediction of actions and so on, and all kinds of things that we are now able to do from activity understanding, human pose estimation, and so on. So given that we're here now at a robotic conference, what does this mean for robotics? Of course, we've also seen a large adaptation from the robotics community in all these egocentric interfaces, especially for robot learning, and especially for demonstration and interfaces for demonstration. There are intuitive teleop interfaces available now that many people have developed. These interfaces provide first-person views that naturally align with robot-centric views. They've really democratized data capture and robot learning through data capture and what is possible. So it could be direct robot control with low latency, like the one on the left here. It could be even AR kind of based setup. It doesn't even have to be a humanoid, like it could be a Franca or an AR Franca that you remap to some actions that a human is doing and so on. So this has been really valuable to the robotics community. What we're trying to do, of course, today is discuss, okay, where do we go here? Where do we go next? How do all these things come together? How do we do egocentric perception and action for robot learning? One big thing that has been very interesting for a lot of the research community recently in robot learning has been, okay, can we try and scale up robot learning with passive human data? Can we take data which is from humans just doing everyday tasks that it would be in theory more scalable, and can we use that to train robots? There's still many of the challenges for this, for like, there's not really action labels available. So you might have information in 3D always, dimensional with occlusions. There is a big robot to human embodiment gap, and how do we actually solve that embodiment gap and so on? What you learn for a human might not quite transfer to a robot. There is also, of course, the whole question of what you should learn in the first place. Should you learn some kind of high-level policy or high-level behavior that makes sense, that kind of get or infer goals from a human? Should you learn low-level manipulation, check out what the fingers are doing of the human and try to translate that to a robot hand? Lots of interesting possibilities. I'm quite excited by some of the papers we have today. Going into some of these things. Is there some kind of intermediate representation where you can just do both? And of course, we're still not done making good interfaces for robotics and robot learning. There's still not there's still scalability. Can we make it more easier? Can we get more data? Can we make it easier for a demonstrator, solve issues like motion sickness, fatigue, and so on? Make things easier. So just to give you, just to warm you up, we have a lineup of speakers and papers that will go through it. We were happy to receive a lot of submissions to the workshop. So the program committee has, with all the reviewers, thank you to the reviewers again, put together this lineup of papers. All of them will be in the poster session later today at 10:30, and 4 of them will have a spotlight talk, 4 or 5 minute spotlight talk just after the coffee break. All right, and just briefly again, this is also on the website, but here's today's program. We're going to start off with talks, then we're going to have a talk by James Ford, who glad you could make it here. He's going to talk about some exciting new updates from Ontario. Then we're going to break for a coffee break and post session at 15:30, which is exactly short. One note, because I had some questions as well. We can't afford to put the posters up already. We have to wait till 10:30 to put the posters up, because our posters are shared with other workshops. So the poster boards are shared with them. From 10 to 10:30 is another poster session with other workshops, and then our workshop starts at 10:30. So we will have to go at 10:30. Probably fight for a place on the poster boards and then move into the poster session. Then we'll follow up by the spotlights. Time is approximately for the 4 spotlights. All of them will have a best paper award. I haven't revealed anything about the best paper award yet. That's exciting. Some pretty nice best paper awards made possible by. Okay, with that, I will stop here and already start with the first speaker. But do we have any questions? Anything from me? Then I'm glad to invite Kristen Brown, let me just introduce you. So Kristen, I mean, most of you might already know, is a professor at the Department of Computer Science at UT Austin. She's also affiliated with Meta. Her research in computer vision and machine learning focus on video understanding, embodied perception. She's part of the Egocentric consortium that we all know of. She's received numerous awards before. She finished her PhD at MIT. She's an IEEE Fellow, AAAI Fellow, Sloan Fellow, Microsoft University Faculty Fellow. She's been an program chair of CVPR, NeurIPS, ICCV, associated. He was the associate editor-in-chief of PAMI, as well as a board member for IJCV. And yeah, we're delighted to be here. Take it with me.
And I want to check real quick if there's anything we need to verify on Zoom, or are we good for setup?
I think
We might need to disable the people joining that.
Oh, yeah, I could disable it offline. I can disable the sound of people. Yeah, I can do.
Great to be with you at this meeting. And the topic today, of course, I really enjoy working on. Glad to share some of our newest work in it. And I'm going to be talking about this motivated from skill learning. And so when I say skill, especially in this venue, I mean human skill, and I mean human skill in order also to help robot skill. And in particular, when we think of skill in video, I'm talking about really fine-grained activity understanding. So things like the details about sports or music or do-it-yourself projects, repairing things, cooking things. These are the kind of domains of human skill where there's a lot of rich computer vision challenges because of the fine-grained granularity of what we really care about to understand that. So in brief, if there was a greater ability for AI to understand human skill, there's two main areas that get affected that we're interested in. And one, of course, robot learning. So we had a good opening already, kind of motivating why this matters. And we can envision the future where we can reduce the amount of physical experience that our robots need because they can learn from curiously through human experience by watching their activity. And this is very important as robots need to operate in human-centric spaces, using objects that are kind of created, also for humans. And then the other major domain that's so compelling is in augmented reality and mixed reality, where we want to be able to have AI assistants of the future that could help you through a daily life task, like the one here, maybe you're building something, fixing something, giving you just the right information you need as you do the task, and understanding the state of your task as you make progress. This will allow new ways to teach people, again, from the everyday things to really aspirational things, like getting better at skills we're trying to perfect. So in the remainder of this talk, there's two main things I'll show you in our results. One, we're going to talk about bridging the ego-exo divide. And two, we'll talk about object state changes. And so this will have to do about major viewpoint change fluidity. And this will have to do about understanding those subtleties about how things transform in time so we know how action is progressing. Now I'm going to break down that first part with some more detail, and we'll talk about these three things in turn. So let's start with the data. So I want to motivate this ego-exo divide. Of course, if we're talking about the actor, maybe this is ourselves trying to learn a new skill, we see our egocentric perspective. If we think about the teacher, maybe the teacher of this instrument, then we see this exocentric view of them. So this kind of doing versus watching relationship. And we need to be able to map between those two to have that learning take place. Similarly for the robots, ego to exo, watch people in exo view, robot operates in ego view. And also in developmental learning, where we know that infants are picking up their own ability to do different actions, having mapped the actions of others, like caregivers, onto themselves. So it's a very fundamental set of viewpoints, widely different in what they capture in terms of what's actually visible in the scene. So in some recent work, we, together with 15 different institutions, put together this data set. You can think of it as like the next evolution or next contribution after Ego 4D. Here we put together EgoExo 4D. And just like it sounds, the main focus of it is to have simultaneously the egocentric view, that's the one you see on the left, as well as multiple static exocentric cameras in the same environment. So these are time synced all together. And furthermore, the content of EgoXO40 is specifically on skilled activities. So as you see some of these domains go by, there are things like sports, dance, music, cooking, bike repair, healthcare. And so you're seeing people of different levels of skill executing all these sorts of activities. And in fact, there's more than 700 of the participants, leading to a total capture over 1,200 hours of video. And the other notable thing about EgoXO40 is the multimodality. So it's multi-view, but also multimodal. And this is by design, and including because of our incorporation of the RA device, where we have the egocentric view as well as multiple other channels of information, including 7 channels of audio, IMU, and very accurate 3D reconstructions, as you're seeing here. That green camera is the ego camera, the red is the gaze direction, and when you see the other cameras white in the field of view in this reconstruction, those are the other exocentric cameras. So I'm kind of showing you this as a hopefully possibly useful resource in coming work, and also inviting you to check out the benchmark tasks that are associated with these data sets that have now a rich set of results coming from the community competing on all these different challenges. Okay, but now let's look into bridging this ego-exo divide. One thing we've been looking at lately is, okay, if we're really motivated by skill learning, we want to be able to take how we see the teacher in our exo view and map what they're doing into our own behavior. You can think of this as an exo to ego translation problem. So can I imagine if I look at the teacher or observe this person here, how would things look from their eyes? And in fact, this is a challenge that we put together in EgoXO4D, and here we're looking at this challenge and providing methods to do this kind of translation. So on the left, here are 3 samples, 3 videos in the exo view, and then what the corresponding true ego view is in the second column. And then on the far right there, this is a diffusion-based model that we developed, what it'll give you for doing that hallucination or translation of the exo view. And the results are showing something interesting in terms of pushing towards generality, although it remains a very challenging problem. But we can see this kind of pixel-space translation being possible. And behind the scenes, kind of the key thing that helped us do this was to surface the hand-object interactions explicitly to the diffusion model. Okay, now that's in pixel space. What I'm going to talk about next is developing view invariant representations. So in exo to ego, that was saying, look, we care about both views. Can we imagine one from the other? Now let's talk about what is very prevalent in many of our modeling challenges, which is to be able to discard the differences between those 2 views. We really want a view invariant feature space where we don't care where the camera was, we understand it the same way. And using paired data like EgoXO or other related resources prior in the literature would be the natural way to set about learning a view invariant representation, right? You can imagine if I have nicely paired data, I can start teaching my model to remove those differences in the viewer, find out what's common. However, this is relatively rare data. As big as EgoXO4D is at almost 1,300 hours, this is actually dwarfed by what we have available in internet scale data, usually on the exo side, where you have hundreds of thousands of hours of content. So there's something here we need to deal with, right? Because on the one hand, we have paired data, it's very high quality, but small. And then on the other hand, we have unpaired data, which is messy and we don't know what to do with it, but it is very big, right? So this is the challenge we've been looking at in some new work, where we want to unlock unpaired data. Okay, we know what to do with paired data. It's very well behaved, very nice and convenient. We could imagine learning a representation where you give me a pair stream, then I can start to push them close together in the feature space. But with unpaired data, pile of ego video over here, pile of exo video over there, even if the domains are relatable, the question is, well, how are you going to train a representation from it? So here comes our idea. We nicknamed our approach the viewpoint Rosetta Stone, because we're taking kind of this analogy of the Rosetta Stone as being this vital, compact resource that tells you how to move between the 2 languages. And so in our world, we know how to have models that look at exo data. We know how to have models that look at ego data. And the question is, can we use these more modest paired resources as a dictionary to start to decipher that ego-exo relationship? Because if we could do that, now it opens up the world of all that unpaired data, right? You can understand how to bring in or rope in that unpaired data to strengthen your models or your representation. All right, so how do we build that Rosetta Stone? So the core element is a translator. And here, in contrast to what I showed you a second ago, this is in feature space, some latent feature space rather than pixel space. And so we have an encoder learned for the any EXO video, any Ego video. And then in this latent space, what we're going to train is a diffusion process whose job is to take a given video and one of the views, so here from the EXO view, and be able to denoise it until it represents and matches that Ego latent feature. Okay, so that means that from any Ego view, likewise, we can use this diffusion model or this translator to hallucinate its EXO counterpart. Of course, that will be possible not only for those samples we observe nicely in pairs, but for any other pair as well. And that's what really opens up this unpaired data. So now you can take any of your Ego videos, like this one here, it has a narration about the activity accompanying it, and using those Rosetta features that map it into its EXO counterpart, along with a text video feature, then we can search among, first of all, we can translate into its hallucinated feature of EXO view, and then we can search among any other real EXO features to find those that are most relatable and introduce what we call pseudo pairs. So a pseudo pair that would combine the hallucinated feature with its nearest real counterparts. All right, so then when you do training, here we're taking a contrastive learning approach, and there's different pushes and pulls we want in the feature space. And maybe the most essential one to take note that's new here is that when we embed any Ego video, we can translate to the EXO counterpart, both in terms of that retrieved most similar sample, which is from here the Ego to the EXO in yellow, as well as its direct translated latent feature from the Rosetta Stone. Okay, so those should be close. Zoom is giving us a little bit of dramatic suspense here on each of my animations. So those should be close, as well as the one that was found to be close, both, and by the way, both on those hallucinated views, but also on, we incorporate alongside the semantics from the language. So we're more likely to impose this constraint of closeness if the semantics from language agree as well. Great, so let me put this into our representation, and we've tackled a few different tasks. So let me show you them in sequence, 3 different things. So first, as the slide advances, we have a cross-view retrieval. So here in either direction, say, I've got an Ego video, I want to find the most similar EXO, or vice versa. And here we're looking at things you would use before this viewpoint Rosetta, and the baselines, including work from EgoAct 4D on view invariant feature learning and language-based kind of semantics-based way to unlock unpaired data as well. And we can see stronger accuracy over here. Similarly, on action recognition across the views, accuracy is improved. And back to this motivation of skill learning here on proficiency estimation, we want to know, given the video, is this a good or bad execution? And we can do this now, 0 shot on Ego video. So here you have, maybe you've trained on a bunch of EXO teachers, which I hope my shorthand makes sense to you. EXO teacher, meaning a teacher we've observed from an exocentric perspective. And now 0 shot, look at the Ego view and be able to do still skill assessment from there. All right, so here then kind of summarize why this, what's our benefit or what are we able to do? It's because if we had only the paired data, this is the accuracy level we could achieve. But as we are now able to, rather than kind of do, be unsure what to do from left to right with adding more unpaired data, now we can really start to exploit it. And so you get this climb in the accuracy as a result. And importantly, that climb was, in our results is still better than what we could do with kind of existing language-based ways to bring together these representations. All right, so then the last thing about EgoAct divide that I wanted to show you moves from view invariant representations to imagining how we could start to know what are good views in the first place. So think about the last how-to video you watched. Here's one from cooking. And what I want you to notice about it is how the camera changes, right? Sometimes that ego view is really helpful. They zoom into it. Other times you're getting the perspective of the full environment and think she's touching in the environment. Other times you're getting her face as she says something interesting. And all of this is done in a way that I think helps us as learners. But of course, it's done in a way that today is very manual. So maybe there's multiple cameras in there, and post-processing, they'll make these switches or do it while they're filming. So that's costly. And so we were looking at this thinking, okay, there is more info in certain views as you try to learn skills from video. But which ones are they? Could we start to predict this automatically? So here's the setting we have. So let's say we have a multi-camera capture of some subject, and we want to know at any given time point, what's the camera we should take? And notice it's going to change over time. Now, the key challenge that we identified over here, I mean, I think there are many, but one that really surfaced strongly is that this would be challenging to supervise. So ideally what we like to have here is lots of multi-view camera data plus labels saying where's the best view at every given clip of video, which doesn't exist, which certainly is expensive and not really that general. So not something you're just going to find in the wild. So we had an idea to address this by incorporating language. And so here's kind of the, I guess this would be the Rosetta Stone, or if you will, for this line of the work, is to look at what our view agnostic language descriptions of the video content to be the thing that we can use to help supervise. So it does happen that EgoAct 4D and other video data sets often will have language narrations about the content. We did this in Ego4D as well. And here in particular, it's view agnostic because the captions, these kind of play-by-play descriptions of the action, were captured with knowledge of any or all of the views. So then here's what we can do. We don't have best view labels, but we have these narrations that are view agnostic at training time. At this time, we have no narrations, it's just video. But at training, we have these. And so what we can do is look at each view of the training sample in turn and caption it automatically. So, you know, maybe this is a view agnostic caption for this content was, oh, the person expects the rear wheel with both hands. And now view by view, the captions look a little bit different. Given one view here, we might caption it, person pulls the rear wheel. Another one, we may caption it, the person puts his hand on the wheel. Okay, so each of these views, something a little bit different is visible. Captioner reacts accordingly. And then what our whole job is during training is to compare this view agnostic caption to each of the view specific captions in turn. And that, you know, say they score, this one is close, this one's not very close at all, and so on. And that's where our pseudo labels come from. Because we've said, okay, if the language produced is consistent with the view agnostic kind of comprehensive description of this activity, then this is the most instructive, most informative view. So this one, say the training sample then would come back saying, okay, for this part of the multi-view sequence, this is the best view. So we train a model, in fact, a classifier that can then look at these pseudo-labeled samples and given a new multi-view video, create a video like you have on the right. So inputs are over here, all time synced multi-view, and then our model is selecting where to look at every given time step. And in this sample, I hope you could see somewhat interesting how I was cycling or, you know, adjusting between ego and exo views. One exo often to see some greater context of what their body's doing on the wall. Ego as they do some of the more interesting motions with the hand up the wall. Oh. Now we have Zoom and a wet computer as well. Actually, I think I need to do something. Oh, thank you. So that's the new one. Okay, then the other sample I was going to show you cooking. Yeah, this is from a data set called Lemma in Ego and Exo. It's making those kind of shifts. Remember the YouTube video I showed you at the onset of this, you know, hopefully we're getting a little bit towards this. Whereas they move about the scene, it tends to be Exo when they start to do some manipulation. Right. All right, so then the last moment here, the other part, we talked in more detail about this, but I wanted to share briefly about the object state changes. Because in fact, here we're doing some new work, bringing this straight to a robot, learning to do some manipulations of objects. So in object state change, we care about representing the transformation of an object as far as the action being completed. So butter can melt, boards could be assembled or cut apart. And this is a great representation on the visual side for robots because it's embodiment agnostic, right? We care about the preconditions, the postconditions, and you need to, find actions, ways to achieve those postconditions. And then we'll be able to see it in video. And so some of the work we've showed at CVPR was about capturing these state changes in what we call progress-aware video frame captioning. Really getting into those detailed components of steps of the action that today's captioning models and even the best models like Gemini or GPT-4o are not able to do yet for this level of detail with the tempo. This is one thing we've been exploring. And the other that'll bring us to our robot is spatially processing object state changes. And so here, the idea is that not only do we know when a state change is happening or that a state change is happening, but we need to know what parts have changed state and which ones haven't. And this really hasn't been tackled yet in the literature. So we were looking at these fine-grained segmentation models that we could construct that would look at a video like these, and here actionable is when the action hasn't been done there yet, so it was red, and green is where we believe it's been transformed. So I hope you can imagine having that kind of layer of segmentation on a video benefiting a robot who needs to know, where do I need to act next? So for time, I will, point you to the paper for a method, but basically we find a way to scale up some pseudo labeling so we can build this segmentation model. And it works like the way you're seeing here. Spock is our model. As it goes from red to green, it means we think that the actions have been completed there. And what's exciting here is now we can move, there's lots of great work on manipulation that often will look at rigid body motion. So moving objects around, pouring one thing from another, opening, closing things, but increasingly a need for some of these messier tests, I guess, even literally of non-rigid object state changes. So smashing and slicing and spreading and coding. And so we used the model I just showed you to build up a reward for an agent that, quite simply knows when the transformation has occurred in a region. And so it can reward reducing the amount of untransformed object. And that's my final slide then, doing this with a robot where it's observing the object as well as the segmentation mask we're creating that's saying where we think things are transformed and where they aren't. And then pretty rapidly with the real robot with reinforcement learning, being able to learn this policy also for novel objects. Because you think how abstract this representation is, you start to be more general. You don't need to know exactly the original object, but you can know that you need to tackle the untransformed areas. And we've been able to do this for novel actions. So here, mashing a banana, so you know where to go to mash. All right, so thanks so much for your attention. I'm glad to have any comments or questions.
So with the ExoView classifier, it occurred to me maybe like climbing versus in the kitchen. They have like very different sort of features that would indicate the switching of the ExoView. Did you find any major differences in different task types?
Yeah, as far as the behavior that takes place, or like the camera switching.
Yeah, exactly.
Yeah, I think that it's definitely worth closer inspection, to get that sense. When we do observe, I think the things you can put a finger on tend to be fairly relatable across to our eyes, which is things about, like if you need broader body pose contact or scene, like body and scene in EXO is what you can only get in EXO, and whereas post manipulation, you get an ego. And I think that's largely what we're seeing transforming between them. But of course, it's open to the model to learn. And so it's worth, continue to look to get that qualitative sense.
Cool. Thanks.
Do you think there could be some value in non-traditional forms of media like films in which there is some narrative which is more egocentric but and skill-based, like maybe a story about a potter or an artisan or something like that? Like these filmmaking has this artistic sense and intuitive sense that they bring in, which is very different from our vision-driven methods, which are more statistical and so on. Do you think that could be a line of thought that would be interesting to explore?
Yeah, definitely. So for the view selection, we come at it from the kind of the instructional video standpoint, say, okay, the objective is, in fact, how we evaluate it is, which view do you need to have most clarity on how to execute this task? So it's kind of instructional how-to. But you're pointing out that, camera work and intelligent camera work can also be motivated by narrative and story and art. Totally true. And, there is kind of great body of precursor work, even much earlier than this for automatic cinematography, where I think there's interest there and, at least aspirations to kind of try to capture that grammar that could be even, that could even be artist specific, oh, that looks like a so-and-so film, that looks like a so-and-so film. It's distinct from the goal as we said it here, but definitely interesting. And, I could take the parallel that, okay, let's say learning from a how-to video happens differently for different people too. And there could be style there that maybe we could start to even learn from in the wild videos.
There is a similar problem in video games, because while you're playing the video game, you keep switching between egocentric and exocentric depending upon what you're doing next. And so there is like a prior of action fed into that. And so, there are these two different modalities that could also feed into this learning pipeline.
I love that. Yeah, I had not thought about a video game connection, but you're right. That's something to really think about.
Okay. I'm happy to welcome Antonino Fornari. He is a tenure track assistant professor at the University of Catania, Italy. He's a member of the English Professor Lab and co-leader of the Live Research Group. His research investigates how intelligent systems can perceive, understand, and anticipate human actions and interactions directly from an embodied egocentric framework to enable assistive technologies, wearable devices that provide direct support to their users. He is part of all the consortiums. He's part of Epic Kitchens, Ego4D, EgoXO4D teams, and he also co-founded the Next Vision University spin-off.
Thank you. I feel my job is much easier now that because she got a great introduction into the challenges and benefits of learning human skill from egocentric and exocentric videos. And in this talk, I'm going to discuss some of the work of my group towards understanding procedures from egocentric video. And the first step to understand procedures is for sure understanding what's going on, so understanding interactions, in particular, actions and interactions with objects. And in our group, we have been working towards this direction for quite some time. For instance, one of the tasks that we have been looking at is understanding hand-object interactions from egocentric video. And this is a pretty data-hungry problem where you need a lot of annotations in order to understand these kind of interactions. And something that we have explored is how to get rid or at least reduce the amount of labeled real data by simulating data or interactions using a game engine. This was Unity in particular. And here what we show is that you can dramatically reduce the amount of real labeled data that you need if you can simulate good data. Also, something that we have been exploring recently is how to abstract from this hand-object interaction into some kind of high-level representation that evolves through time thanks to structured representations such as graphs. And we introduced what we called egocentric actions in graphs, which are inspired to graphs, but focusing on the object interactions, and so the objects that are in interaction with hands mainly. And we provided this kind of representation by providing labels for the Ego4D, for a subset of the Ego4D dataset, where you have this spatiotemporal evolving graph that represents how activities unfold through time. And what we show is that this kind of representation can be useful for long-term understanding tasks, such as short-term action anticipation, long-term action anticipation, and summary generation. And maybe one of the tasks that you can think of when it comes to understanding human behavior is temporal action segmentation, where you take as input an untrimmed video and you want to break it down into specific segments where people carry out some activities. Now, this task has been investigated for a long time, and we can imagine how there are systems in place in different domains which try to address this kind of task. But this is usually done in exocentric settings. And now you know all about egocentric and exocentric. So these are settings in which you place fixed camera, you collect video, and you run your algorithm. But we envision this other scenario in which you would like to be able to bring these capabilities to an egocentric camera. So a theme that we had in our lab is how do we bridge systems across views? Now, and with this work, what we thought is that let's consider a scenario in which you have exocentric videos which are labeled, you train your system, and it is working well on this exocentric data. And then if you test it on egocentric data from the same scene, of course, you cannot expect to have the same level of performance because of the domain shift. Now, what you usually do in this case is collect some new egocentric data, label the egocentric data, and fine-tune the system. And this is doable, but it is also costly. Something that instead it's straightforward to collect is unlabeled, but synchronized and paired examples of egocentric and exocentric activities. So the idea is you already have your fixed camera, you place another camera, which is an egocentric one, you perform a synchronized recording, and now you have these synchronized pairs that you don't have to label. And what we show is that we can adapt models by just using synchronization as a form of supervisory signal for adaptation. And of course, then we recover performance on the egocentric videos after the adaptation. And this is pretty straightforward. We do a very simple thing. We perform feature distillation and model distillation. So we perform knowledge distillation where we have a teacher which looks at exocentric videos. So this has been trained with a label, labels. And then in the adaptation stage, we feed a student with egocentric video and we perform feature distillation so that now the student mimics the features extracted by the teacher, and also temporal action segmentation model distillation. So we basically align the internal features of the temporal action segmentation model. And the surprising thing is that when you do this, you basically recover supervised performance without any label in the egocentric views. So just synchronization allows you to avoid collecting labels altogether if you can, collect good synchronized pairs. And something that we also show in the paper is that you don't need perfect synchronization for this to work. But beyond recognition, beyond understanding what's going on, we need to get a better sense of what people are doing, what are the next steps, and if people make mistakes. This is another topic that we have been recently investigating, detecting mistakes in egocentric video. And this is very relevant for different things. Detecting user mistakes is fundamental for contextualized AI. If people are making mistakes, you want to alert them, you want to give them suggestions. The problem is that one way to address this is in a supervised way. So you label mistakes and you train a supervised method to detect mistakes. This is costly, expensive. This requires domain knowledge, but it's also very limited because mistakes by their own nature, they are open set. So even if you do a good job and you can characterize a set of mistakes, you can expect that at some point a new mistake arises because there are few ways of doing something in the right way, but there are plenty of ways to make mistakes. So in this recent work, there is a collaboration with the University of Rome La Sapienza. We proposed a simple approach which has two modules, a recognition module where you take as input your video and you have an online action recognition system which recognizes the actions happening in each frame. And then you have another module which takes this abstract representation of what has happened in the past in the form of past actions and tries to predict, to anticipate the next action. We do this with a large language model because this is training free, but this could be done in different ways. And now the hypothesis is that if everything is fine and if there is no mistake, then the next action is going to match the action that we are currently observing. So we trigger a mistake if the two predictions do not match. And the pros of this work is that it works online. It is a one-class setup, meaning that the training time we only see correct executions, we never see mistakes. But this requires supervision in terms of segmented action. So you still need to have a taxonomy, you need to label actions, and you need also to have a good action recognition system. And we wanted to go beyond that. So in this recent work, we thought that maybe we could use gaze trackers as a form of additional input that you can have both a training time and a test time. And we know that gaze gives you an idea of what people, the behavior of people, what people look at is very important, and it tells you something about what they want to do or what they're trying to achieve. And so we wanted to leverage this. So we wanted to leverage the gaze tracker test time as well. And we observed that when people perform actions in the correct way, there is little variability in the gaze patterns. If you average all gaze patterns for all actions of the same time when there is no mistakes, you obtain something close to what you see here on top. If you do the same for wrong execution, so this is the same action, but these are wrong executions, you get a lot more variability. So we thought that maybe it is harder to predict gaze in the presence of mistake. And we proposed this simple scheme where we take as input through a wearable device with a gaze tracker, we take as input a video and a trajectory. Now we keep only half the trajectory and we throw away the other half. And we train a model that we condition, that looks at the video and is conditioned on the partial gaze trajectory to reconstruct the remaining half of the trajectory. Now, this is easier than predicting the whole gaze on the video. And also the conditioning will tell us the model something such as what is the expertise level of the person or what is the goal of the person. Now, our hypothesis is that if the person is making a mistake, then the other half of the trajectory is not going to align what we are predicting. So similarly to what we saw in the other work, we compare the predicted trajectory and the grounded one. And if there is a misalignment, then we trigger a mistake. So same concept, but we want to get rid of the taxonomy and of the action recognition system. Now, what are the pros of this method? It can work in a 1+ setting as the last work, but also in an unsupervised setting. We only need to train the gaze completion module, which is this one. And you can train it also on a mix of correct execution and wrong executions, assuming that the wrong executions are going to be rare in the set. And also this is domain agnostic. We don't even need to define what a mistake is in our settings. This is an example. There is some flickering in the blue dot, but it's a visualization issue. So please take the expectation of the blue dots. And what you can see is that in a correct execution, the blue dot is always around the green one, which is a ground thing. While instead, when people make mistakes, there is much more variability, and the blue dot jumps. Okay, these are tables with results, but the main take-home messages here are that our model can recover in 1+ setting supervised performance. So we have results which are very similar to supervised methods. And this is mainly because it's very hard to detect mistakes in a supervised way. And also, even when you train in unsupervised settings, you lose some performance, but it still works if mistakes are rare. And this got the first place last year at the EgoGIS workshop for HoloLens Mistake Detection Challenge at CVPR 2024. But beyond understanding mistakes, another interesting topic is extracting the structure of the procedure. And to understand what it means, we need to take a step back and think of what the procedure is. So we can see a procedure as some goal-oriented activity where people try to achieve a given goal and they have to follow a given set of key steps. Now, this is structured in the sense that not all possible orderings of these key steps are valid, but it's not that structured, meaning that there is not just one possible ordering, but many orderings are possible. One way to describe this kind of partial ordering imposed over key step is to use a directed acyclic. There are different variations in the way that you can define these. These are often called also task graphs in the literature. And this in particular is a dependency graph. Something like that is used, for instance, in package management systems, where basically the nodes represent the different steps that you can take, and the edges represent dependency. So this edge tells us that in order to crack an egg, you first need to get a ball. And these edges represent that in order to mix the mixture, you first need to add all ingredients. Now, a graph like this, if you can perform a visit of a graph like this, respecting the rules, and this is called the topological sort of the graph. And all topological sorts represent all valid execution of the procedure. So for instance, get a ball, add water, add milk, crack egg and mix are valid visits. Get a ball, add milk, add water, crack egg and mix. It's another valid visit, so you can switch the ordering of these nodes, but you cannot just jump from get a ball to mix or skip any of the nodes. Now, ideally, if we could extract this kind of graph directly from videos, this could enable a lot of applications by simply encoding rules-based systems on this graph. And this is what we wanted to do. And this has already been investigated in the literature. There are some works trying to do this. And they show that if you can do this, this can be useful for downstream tasks. But the works that we investigated at the moment where we were working on this were based on dynamic programming or some heuristics. Ideally, you would like to have some gradient-based method, some loss function that can learn these graphs. And this is what we tried to do in this recent work that we presented at NeurIPS a couple of months ago. So the idea is that you have an observed sequence, or better, a set of observed sequences, and you want to learn a graph from there. We're going to represent the graphs and adjacency metrics because it is more, say, learning friendly. And the idea is that if you could estimate the probability of a sequence, so let's say S, A, B, and E, given the graph in a differentiable way, then we could perform maximum likelihood on Z. So we fix the sequences and we perform gradient descent on Z. Now, the problem with that is that the sequences are non-differentiable string of symbols, so it's not straightforward how you would define that. And what we came up with is that you can factorize that kind of probability in different ways, and we choose the most convenient way for us. So we factorized it in a way that on the left, you have the current step, and on the right, you have the past steps. And if you do that, then you only need to estimate this probability now, where Ki is the current key step and Kj is a set of previous key steps, right? And this answers the question, what is the next step? So we want to maximize the probability, let's say the likelihood of observing what we have in the tail set. We define this in a very straightforward way as the number of favorable cases under the number of possible cases. So let's make an example. Let's say that you're observing S. What is the probability of A given S and Z? Well, A is a possible case because we could visit A, B, or E. A can be visited because it depends only on S. B can be visited because it depends only on S. And E cannot be visited because it depends on A and B, which are not visited yet. So this probability is going to be 1/2. Now, there is a way to write this in terms of the numbers of the adjacency matrix, which turns out to be just sums. So it's differentiable, of course. And if you do some math, so you take basically the negative logarithm of this to perform the standard negative logarithm, we obtain a differentiable loss, which is a maximum likelihood loss function, which is a contrastive loss in particular. And we use this to perform gradient descent directly on the graph space, which is the space of all possible adjacency matrices. So we randomly initialize these metrics and we perform gradient descent. And we also use this loss function to drive the learning of more complex networks. So this is a network which takes as input descriptions of key steps, either in the form of textual feature or video features. And at each forward pass, it obtains a dynamic adjacency matrix, and we can supervise this with our loss function. And the advantage of this approach is that at different forward passes, you can have different graphs. So we can train different procedures all at once. This is what happens during training. So as you can see, the complexity of the graphs drops down. So the number of edges that you see will reduce until we converge to some structure which encodes the procedural constraints of this procedure. And this structure captures things such as these chain-like structures, which tells you what are the preferential path to go from start to end, but also these parallel threads, which tell you what are the different variations, the different ordering variations in your step. Now we say that what the problem is that now that we have this, we just need to encode simple rules of these graphs. So for instance, let's say that you want to do action anticipation. If you observe get a ball and crack egg, what can you do as next step? Add water, add milk, but you cannot mix, okay? Or for instance, mistake detection. You observe mix, you already observed in the past get a ball and crack an egg, but if you didn't observe add water and add milk, we can say this is a mistake, a procedural mistake, an ordering mistake in particular. Or we can reconstruct the history of past steps. So for instance, if the user is mixing and is asking us, is this the correct step? We can say, well, check if you already did all these things because you should have done those. And by encoding these things on EgoAct4D, we show that we obtain big gains over baselines on 5 different procedural tasks. And this also got the first place at the EgoVC EgoAct4D Procedural Understanding Challenge last week. All right, these are more detailed results on mistake detection, which is the main task that we investigate with this kind of representation, on two data set, which are assembly 101 and epic tent, where we also compare with the previous work that is shown with Prego. And this is more flexible because in Prego, you only predict one possible action. And in contrast, here we are saying, is the action that we're observing feasible among the all possible actions? Okay, so this concludes the talk, but before concluding, some quick take-home messages. So I think that understanding procedures is key for wearable assistive applications. I think it's also important for robotics. We're not doing robotics directly, we're looking at this field. I think that for robots, being able to understand what is the correct execution of steps can be useful for different ways to mimic the human, but also to provide support for the human, for instance, anticipating the human's next step. I think we need to move beyond understanding atomic actions towards this more long form and procedural level understanding. So understanding the relationships between steps and understanding what comes next and if there is a mistake. And also these human and interpretable holistic representations of procedures, I think they have a big potential. Of course, they are limited in some sense. We probably need to mix them with neural representations. But as you can see, once you crack one of these representations, you can tackle lots of tasks and it's easier to generalize on a lot of things. So I think there is an interesting potential. And this concludes my presentation. If you're interested, the slides are at the QR code. I'm happy to take comments and questions.
Maybe before we start, for me, mistakes are also very interesting because often for a robot, what the whole part of the data set that you're most interested in is how the human recovers from an accident. And that part of the data is essentially what you want to go about. Has there also been some kind of challenge or something on like recovery from mistakes?
Not there overall, not in the centrifugation, but that's interesting actually. So in the work that we did with the University of Rome, we actually took another view on that. So the point is that if you see that from a video understanding point of view, if you can observe the recovery from the mistake, it's very easy to detect the mistake, which is why we thought you should not do this in an offline setting where you can observe also the feature. So we're gonna stop at the first mistake. And I mean, this relates to what you say, because the reason why we stopped at the first mistake is because recovering informs you on the mistake. So that's an interesting piece of information that, I mean, I agree. I think it's interesting to look at.
This be the dual.
Yeah, right.
Just to add to that point, because in assembly, if you're assembling something and you make a mistake, basically disassemble it. In certain cases, not so much. States are right. They're not going to. I think the most abstract because I saw a line also later in the results showing LLMs which do similar things, right? Do you think, because I would assume that this knowledge is implicit always in LLM already. Obviously, having the graphs is a much more efficient structure. How do these two compare? Why is it that LLMs are not doing this?
Right. Okay, so these are results with LLMs. But the disclaimer is that this was ages ago. I think it was less than 1 year ago, but still we are using I think Llama 3.1. I'm not sure what happens if you try now. We should probably. Because what we did here was reconstructing the graph asking LLMs, I think questions such as, is there a dependency between these two key steps? And we were iterating over all possible pairs. And then after that, you obtain a graph, you do transitive closure so that you get rid of all the redundant edges. And this was suboptimal at the time. But really, I mean, Llama 3.1 does not compare to anything that's out there. Maybe we should try with the Gemini, I don't know, 2.5 Pro or something more state of the art. But then I think that's something that needs to be also investigated, how much these models, without any specific training procedure, they learn this kind of cause-effect relationship, because this is really close to the cause-effect relationship. I think that's interesting.
So in the one you showed, like with the task graph, like you have different nodes there, right? Or so each node is action. How you get the action?
So you mean, how do we define the nodes?
Yes.
Yeah, we are leveraging existing taxonomies. Of course, that's a limitation of that kind of approach. So it means that you live in a closed world where you know which actions are possible. And we start from the assumption that we have a sequence of steps.
So you already know the possible steps there.
Yeah.
So another question is like for a lot of tasks, like as you said before, like assembling the furniture, there is a lot of like repeating tasks, like
Yeah.
putting some screws, right? So in language level, they're almost the same, but maybe they're not that same. So how can your method handle such cases?
Right. If I got correctly your question, maybe you have the same, a similar description for two actions, but the visual nuances are different. So people visually do slightly different things. Yeah, this is something that is not taken care of in that kind of representation so far, which is also what I have in mind when I said we need to mix this with neural representations. Because ideally, you will like, I mean, a neural representation is the best way to capture that nuance. You could try to get, let's say, a textual representation very accurate, but I mean, eventually you need some kind of neural representation to distinguish those two executions. And ideally, by mixing those, you can get the strength of words.
And also like, because in the data, like you recorded for the data set, I mean, you cannot avoid making mistakes, right? So you will mix the data with mistakes. So how that will influence your final result?
Right. So in this case, in the case of graphs, we are considering data without mistakes, because otherwise that will end up in the final graph. So let's say, well, I think, I'm not sure we have a thorough investigation of this, but we had some experiments in the supplementary material where we added noise to the sequence to see how this affects building the graph. And it does affect building the graph. If you have very little noise, you can still recover a reasonable graph. But if people systematically make mistakes, what you're gonna learn is that there is a correct path. And so you're gonna learn that in the graph. But I think this is largely unexplored at the moment.
I know.
Jai the Dean's Chair, Associate Professor at the School of Computing at the National University of Singapore. He's also currently a research scientist at Meta Reality Labs in Zurich, Switzerland. Our research group centers on video understanding, digital humans, and he received the fellowship by NRF and grants from the MOE Singapore, AI Singapore, and various industry partners. We're very happy for you.
Thank you. Introduction. Do I need to be, I should be sharing to, does it need to be plugged in?
Oh, yeah, it does not.
Or I made a mistake.
No,
No, it's
if
from
you'd like to,
Zoom,
you
right?
can
Yeah,
do
yeah.
that.
No, I understand. Okay. My talk has a lot of common topics with the previous two talks from Antonino and Kristen, so I think I don't need too much context. but I think the focus of my talk today, actually, even though we're also talking about understanding procedures and egocentric video, I want to focus on one aspect, which is about the streaming aspect of things. So slightly different take. People can hear me, right? All right. So the premise or the application setting we're looking at is these augmented reality assistants. The idea is you have this video feed from your augmented reality wearable here, and you're asking this virtual assistant to support you in some task. So in this example is your say, I want to make breakfast. What should I do? Right. So this is a bit of a trivialized example. I think we all know how to make breakfast, but you can imagine which direction this would go. And some key features or aspects of this problem setting is one, in terms of visual input, we're dealing with video. So we really have a lot of human object interactions and lots of background distractors. We're really centered on these procedural activities. These are the ones that are most interesting, which we think will benefit from having assistance. And then in terms of robot learning and imitation, I think just to place it a bit more into this workshop and also with respect to this talk is how can we do this on the fly in real time? So this is the key focus here. The key distinction I want to make here about streaming setups versus typical offline setups is that we only have this online context. And so in this offline setting, we have access to everything, maybe this entire procedure, both the everything I've observed up to that point. If we make a mistake, then we have a mistake, we have a correction. And this gives us much more information than this online setting where we only have access to whatever has happened up to that point. So you can imagine this makes the whole learning problem much more challenging. I have 3 parts of this talk. I'm not sure I'm going to cycle through all of them, time pending. So the first is to talk about architectures in terms of how should we design our algorithms, architectures specifically to capture really this full range of context. Because if I only have this past information, I want to use as much of it as possible to support whatever it is that I'm trying to figure out currently. We want to talk about visual encodings to design features that are both efficient and discriminative. And the last setup is to then incorporate this into open world settings now, where maybe we don't even have any training, but thanks to these large foundation models, this is a reality now. We can generalize to real world settings in an open way. So we jump to the first one, which is about the architectures, and specifically focusing on capturing these long ranges of temporal context. Just to give some contrast, how much context we need is obviously task pending. So if you don't need much, then our classic ways of doing this sliding window style for the slightly older members in the audience here, I think this term is not even used anymore. You basically just scroll along, and this is this, I'm going to call this now only type of model, but it's a sliding window. Basically everything that I need to make my decision is contained by itself, then I can throw it away. And in these longer contexts, of course, I want to keep everything, but then you run into constraints, right? So your window cannot be infinitely long into the past. So what we want to do is basically process something and store it somehow into this memory. And then as you progress, you have this memory that also supports your current window decision. We call this now plus memory model, right? And this gives you better long range support to store the past as context. And then there's varying amounts of past that you can store depending on your application set. And I think this is a fairly common architecture that's being used now for this streaming processing. You have everything that you observe up to a certain point. What I'm visualizing here with these colors are these different, to indicate different actions that might have occurred. And what you do is you want to compress this whole range of observations into the past, into this long range dependencies, into your memory. And at the same time, you have a slightly different setting for your short-term immediate observation, because usually these are the most important and informative at that moment for decision making. And then you want to merge the two. And then depending on your constraints, you can either dynamically adjust these encodings of the memory or compress it in some way. And to keep this portion of the short term basically to be online, we apply this causal mask. Merge the two into some sort of attention setup or your favorite transformer, and then make your decisions. So you tend to the long-term memory with respect to and then there's this third element, which is this idea of future context, right? Because if you recall in this offline setting, we have access to everything both before and into the future. So in this online setting, if this future information can help us, maybe we can kind of hallucinate this future information to support our decision making. And so that's what we mean by saying anticipation, which is trying to solve what is happening into the future. This will give us some additional pseudo context. And again, so we can anticipate or hallucinate this future information and then also use that to support our decision making as well. And so then one thing that I wanted to highlight here, this is some recent work that we presented at CVPR now, was we found that actually setting up these types of learning strategies for such architectures is non-trivial. And one thing we distinguished was where you have if you have discrepancies in training versus inference, then it can cause problems. We have to design our training strategies very carefully because usually when we train, we're training from offline data. And so what happens is in standard sampling strategies, what we end up having is these varying amounts of short-term context. You basically take the same chunk and then I'm going to sample from it in various ways to simulate many different samples. And depending how you sample, you might end up with different amounts of short-term context. And this actually causes discrepancies in your training. So if you can imagine on the y-axis is your loss and on the x-axis the amount of short-term context, you can see there's a huge imbalance here, which because of the amount of context that you're exposed to, it disrupts your learning, your future learning. And then the second point that we actually uncovered was that in this hallucination of future context, this anticipation, this is often done in a non-causal way, and you end up having information leakage as well. And this information leakage is also, you can uncover in the feature training as well. When you look here, this portion in the middle, it actually has the most benefit. And this is because it actually in learning generator for this anticipation, it got access to future data. So this is some information leakage there. Because we're able to diagnose these discrepancies in this mismatch between these online, between training versus testing settings in online frameworks, it becomes fairly straightforward to provide a nice fix for them. And so for our short-term context, we give it some extra information to balance out the this intermediate dependency. And we can also fix this leaky version for anticipation to support, to ensure that this is not causing a mismatch as well. And so then if you look at the same plot there, you can see our pink line, our newly defined. I think the takeaway here is basically to say that, you know, even though we are, we're interested in having online systems and streaming systems, we have to train them in a very careful way, especially because we're learning from offline data. And sometimes the small details and small nuances will cause disruptions as well. Okay, so I'm going to jump to the second part, which is to talk about efficient encoding and how to design features which are both efficient and discriminative. And the key focus here, of course, is that in these egocentric settings where you have your wearable, we're mostly targeting hand-object interactions. And on top of which, the objects that we interact with, especially as Kristen had shown in the first talk, is that these objects change in state. And this progression of when it's whole versus when it's cut, it can look very rapidly different, right? And so this transformation also might differ for the same action, right? So depending on how I cut my eggplant, maybe how it looks, whether it's cubed or slices or well, slices and rounds, they all look very different, right? So previously we showed how in slightly older work where the best place to reason over these things is maybe not at this very high level to say, you know, the eggplant is already cut versus this very low level, but this intermediate level of features, and then we do some reasoning at these intermediate stages and do some relational modeling. And this gives us a lot of benefits in terms of capturing these state changes, transformations. So that was in terms of the fine-grained aspect. Now we jump to the efficient encoding. And here we experimented a little bit to say, well, you know what, I'm interested in understanding these human object interactions in a very efficient way. But maybe I don't need to process all of this video data all the time. And the idea here then is that we can have very efficient hardware design setups for doing things like estimating the hand pose, for instance. And also looking a bit more into the future as well is maybe I don't even need to estimate these hand poses with visual data. I can have some small wearable device or maybe your watch, you can get some approximate pose and use this pose information to support or augment the RGB. And then the RGB, you can be very sparse, be very selective in what you want to process as video or as images, and the rest purely comes from sensor data in terms of pose. And again, we can show that, so this is this assembly with the toy assembly here. Supporting sparse RGB frames along with a stream of dense poses is a very efficient way to combine to estimate what the actions are. And the takeaway here then is that using hand poses is also a nice way or a very efficient proxy to do this fusion instead of brute force video model on all the views or your egocentric view only. If we switch more towards some of these visual foundation models that we have in terms of capturing these interactions over time, what we found in more recent work is that using certain visual encoders, which are very language aligned, tends to disrupt, you lose some of this fine-grained visual spatial alignment compared to, say, the Dino V2. And I think this is very common now that we see in other papers as well. The gist here, and we also showed in our work, was that if we use encodings which are trained with the sparse language supervision and language alignment like CLIP and SIGLIP, then you have this collapse in terms of this information. Here we call it temporal collapse because we can't distinguish these fine-grained actions anymore, but you also lose the spatial alignment, right? Whereas things with dense supervision tend to be more discriminative. And I think some of the newer works coming out, for instance, with the perception encoder are showing similar things as well, where we want to target these middle layer features, which are still also spatially aligned. And so we can plug this in if we use these dense feature encodings, for instance, like Dino V2. And we can put this into a framework which really focuses on the hand and object itself. So in our work, we designed a dedicated version of Q-former for the hand and the object. Then so instead of the previous Q-former, we designed this dedicated hand and object queries for the then we can get much better improvements in terms of performance, right? In terms of enhancing these fine-grained interactions. And so this is our work on this. So we recently won second place at the fine-grained key step recognition. So I'm going to jump to this last part, which is how to incorporate large models for open world settings. This is to rethink a little bit about this whole architecture of long-term and short-term past. So we want to plug in an LLM or some other visual foundation model into this setting. One way we can do this is to say, well, in my short-term dependencies, I can feed in my visual data into the LLM, but the challenge is also that the LLM tends to be quite expensive, right? So we don't want to do this all the time. So one way we can handle this setting is to say, well, in my long-term context, I don't need to compress this as tokens anymore. Maybe I should verbalize this, right? Because this is the historical information that I want, but at the same time, I want to preserve some visual encodings as well from this recent past. This is the general context. And one thing we can leverage, of course, is because these activities are temporally connected, verbalizing them and talking about this procedure will significantly reduce the amount of tokens we actually need to consider. So this is our new architecture, where it's called Provide LLM. It's a procedural video LLM. So the focus here is really on these procedural key steps and being able to predict. And one of the key points that we show here actually is to adjust the past into this verbalization historical context, And a second thing is to actually how to store this, instead of storing this as two memories, this long range memory plus the short term, to interleave the two into a single memory. And this actually gives us a lot of efficiency boosts. So the idea is here, I have my visual encoder that observes things, and it gives me the action. And then once the action is finalized, then I can verbalize this, and then I don't need to, then I can store this in language form instead. And then I continue storing the visual tokens and proceed until eventually, when you run out of buffer, you have overflow, then you can start discarding. So we have our long range interleaved. These are these language tokens interleaved with the short-term visual observations, the two together. And one of the big advantages of doing this, of course, is that it's very efficient in terms of the token count. So we have almost sublinear scaling with respect to the video length. And on top of which we can compress very long ranges of context that into short amounts of space. Yeah, so this new provide LLM that we have here is a generalized streaming model, I think. So here we're looking at this in the context of procedural activities, but I think this could be adopted to many streaming setups that basically look at, you have your LLM to support general knowledge, and you have your visual data at the same time. Then depending on what you query, of course, you can recognize the current one or anticipate future actions and so on. So here it's streaming along. So I encourage you guys to check it out if you're working in similar areas. So I think this is roughly the summary of how do we capture long ranges of temporal context in terms of architecture. We looked at how to use memory and anticipation frameworks, but remain causal. And so there's some tricks here of being careful not when you do your training. How can we design features that are efficient and discriminative? We've opted to center on these hand and object interactions. This is basically customized to the application. And then, of course, the last point is how to incorporate large models for open world settings. We have to be selective about our use of LLMs to remain efficient. I just want to give a little bit of plug at the end of the presentation for some of the recent work that we're looking at in terms of these assistant settings. One is to incorporate text information into the QA. So this is a work that we presented at CVPR this year. And the idea here is when you ask your VLM some question, sometimes maybe actually having some text information will support you, right? So when I see here the scene, what are these people doing at the audience? They're listening to a talk, but which conference are they attending? Then we can identify from the name tags that it's actually RSS. So this is type of information. This is yet another way of incorporating information into the VQA setting. And additionally, something happening here, yeah. Additionally, we are starting exploring also, so we've talked about assistants here. I think having assistants to help us make breakfast is all fine and good, but I think in the bigger context of assistive tech, I think where this could have immediate impact also is to support the visually impaired and the blind. And so we're trying to push in this direction as well. So recently we collected a data set from, these are content creators, like visually impaired and blind content creators, which at first I thought was a little bit of an oxymoron, but there's a whole community out there and they're very passionate about this because they want to share with the rest of the world to, from their perspective, how it is that they navigate certain scenes and so on. So we've taken content from this and then also sourced dedicated question and answering pairs to support this community. It's also, yeah. With that, yeah, I'd like to acknowledge my students who did all the hard work in what I've presented today. I think to some outlooks, one thing which we didn't really touch on, but I think is impacting our work a lot is this idea of looking at start and end times for actions and also progression. This is inherently ambiguous, right? And we don't have good answers for this. At the moment, we just kind of peg it to annotator, start and end, but I think this is something that we should factor. How do we fuse different modalities into our decision making. All these new devices, they're loaded with a lot of additional sensors, so that I think this opens up very exciting areas of exploration. What we've seen still is that this ego viewpoint dependency still needs some specialized visual encoders, but maybe we can slowly also exocentric data, as Kristen had shown earlier. And how do we navigate efficiency and performance trade-offs? I think this is the big key question that we need to answer in our streaming setting as well. And one last part, which I didn't touch on also, but I'm excited to explore, is this class imbalance issue, actually. I think when we show this nice segmentation graph with the different classes, I'm not sure this is a totally fair representation of what's happening in a lot of the background. So how do we handle this background class to prevent false positives? Thank you.
Any questions? So on the provide parts, so scaling sublinearly is great. What about constant memory? I mean, if you are going to ingest the whole visual perception of a person over their lifetime, maybe sublinear is not enough.
Yeah. I think we've been pushing on this front. What I would hope to do is to make it a one-off, but I think this has very much context with respect to the scale of the actions that we care about, right? You've seen trends now, everybody's talking about long range understanding, right? And how can I make this infinitely longer and longer and longer? But I think this duration and length of what we look at in terms of context should be placed relative to what I'm interested in. And if I'm only interested in a very specific moment or a very specific setting, this is more of a I would argue this is more of a retrieval problem. I don't need to understand your last 48 hours to know that in that one moment when you left your keys at the door, I just need to search for it. Right? Well, we know certain events with respect to the day are contextualized when you have keys and so on. So I think there's still some imbalance. So in that sense, I think sublinear is all right because I don't need to store images for my entire class to understand the context of this exchange.
I also have a follow-up question for me. When you verbalize and you save, let's say, textual information, it looks like there is a trade-off between the nuances that you're going to store and, I mean, the memory that you can save.
Yeah.
How is that handled? I mean, don't you risk to miss some important details that later you cannot recover anymore?
Yes, yeah. So this this is kind of open work in the future. Right now, we're just doing first in, first out type of maintenance in the memory itself. So once I reach my buffer, I just throw away the oldest stuff. But I think there's obviously more clever ways to make.
Awesome. That's the next speaker again.
All right, awesome. Awesome, we're setting up this. My name is Stanford. I'm one of the co-organizers here at this workshop. So for the next few talks, we'll kind of switch gear to talk more about robotics contracted by understanding the eccentric videos to solve problems. Simmer is a teacher student for design. Also happen to be one of my students. So he has done excellent work in this area. One of the interesting sort of pioneer work learning communication learning from Egocentric videos called EgoAct. And here this is the talk about seeing that it's quite interesting. So I'll let you talk the topic.
Thank you. Sorry, I'm just getting the presenter. Okay, so yeah, first of all, I'd like to give a big thank you to Danfei for inviting me to give this talk in the first place. He's been an awesome advisor of mine at Magic. And so at first, what we really planned to talk about here was just my recent work, Ego Mimic. But it's been a while. I decided I want to talk about something a little bit different. So we last minute decided to change the topic a little bit to this. What if I drop out of my PhD and start a data collection company? What would I do? And so this is mostly a hypothetical question, but it leads towards these two important questions that I don't need to answer if I were to do this. Take the picture then. Give me a second, The two questions are, what data is valuable for robot learning? And then how do algorithmic advances change the relative value of data? And so first, I'll give some context. I'm talking about this in the context of robotics. And so, data-driven robotics, seems to be one of our best, chance towards, dare I say, physical intelligence. And it's shown us some really incredible results on tasks where we have sufficient data. And so, the data that really powers breakthroughs like this sort of look like an image observation, a state, an action, and these might be labeled with language. And then very roughly, the goal is to now take all of this data, right, and ingest it into a really large model and maybe train some BC policies on it. And so most recently, these models have been large vision language models, and they've been trained on internet scale data. But now we're kind of hacking them to start ingesting robot data, right? So we want to start feeding in robot data and get this VLM to start outputting robot actions for us. But there's a key issue. Unlike before, where this VLM was trained on really cheap internet scale data, the data that really derives performance here is very expensive robot teleoperation data. This requires like human hours, someone standing at a robot teleoperating. And so even if you're at a company that's willing to spend a ton of money on collecting data like this, the problem isn't solved. You need to decide like what data is the most worth it for you to collect, right? For each dollar that you have to spend, where are you going to allocate it? And so I think it's very up in the air what the answer to that question is, but I think I'm going to give a little bit of an overview of where I think we are so far. So I propose that we think about data on a few axes. These two axes here, I think, are usefulness and cost. Let's go through like some of the kind of common modes of data collection so far. So in this wave of data-driven robotics, the first data source that we should probably talk about is robot teleoperation. And so robot teleoperation is undoubtedly very useful. It's the only data that we can really like put directly into our model to actually get performance. But then there's costs, right? To collect this data, you need to, to collect this data, you need to, have robots, maintain like uptime, think break all the time. And so basically, I think that puts robot teleoperation data somewhere here on our graph. It is the most costly, but it is also the most useful. The one thing that you can directly use to train your robot. Then this tries to bring us to more creative and cheaper forms of data. So I'm sure all of you guys have seen things like Yumi and a lot of very closely related work. And the idea here is to keep the morphology gap the same, but now you can have a human who's holding these things to collect this data. And so it is extremely useful still because you can use it for pretty high efficient code training or sometimes even zero-shot policies. But the cost is the cost is much cheaper than robot teleop data, but it's sort of not as cheap as it could be. And so you can imagine that if you wanted to collect this data, you still need to pay people to go out and do these things, and you have to pay them enough to kind of go over the inconvenience of not using their hands, right? You wouldn't really want to go about like going about your actual job with Yumi groupers, or like paying a chef to go throughout their day to cook an actual meal with Yumi groupers is a bit more of a challenge. So that makes me put Yumi somewhere around here. It is considerably cheaper than robot teleoperation data, but it comes at a little bit of a hit to usefulness. Okay, so now obviously we're at this we're at the EgoAct workshop, and so we should be talking about human data, right? Where does human data? But no. Okay, we obviously just have to talk about human data, and so I think for a long time human data was thought to be useful, but only for things like learning better visual representations, or maybe thinking about object affordances, or extracting like high-level semantics. But I think our work, EgoMimic, helps challenge this at least a little bit, and make the argument that we ought to use human data for as if it is really robot data. And I think we were able to increase the usefulness a little bit by thinking of it in this way. So I'll give a little bit of an overview about our work EgoMimic. So I think what we realized is that with the right set of sensors, in our case, it was the ARIA glasses, that the data that comes out that you can report from the human egocentric perspective actually really closely matches the modalities of robot teleoperation data. It has these frontward facing RGB videos as well as hand tracks and head tracks. And so when you put this all together, it really resembles what you see in like an imitation learning data set for robotics. But to make this data super useful for robot learning, there were some gaps that we needed to bridge. So we found that matching, that using a humanoid robot as well as matching the camera sensor between these two embodiments made it so that the data we collected from the human really closely matched the data that was being recorded on the robot. And what that enables is really seamless code training. So EgoMimic was able to just take both of this data and ingest it very uniformly. So I'll give a bit of an overview on like just how we did that. So, and I think, what is really new about EgoMimic is that we take the formulation of just assume in your batch of data, you have an equal sample of human and robot data, and you're going to treat it pretty much in the same way. So given this batch, you'll take your poses, you'll individually normalize the proprioception, you'll have everything through a shared vision encoder and policy network. And then ultimately, you'll just output 2 actions depending on the modality. You're going to output joints for just the robot and pose for both human and robot. And so you can basically see that almost the entire model, like 99% of parameters, are shared between both human and robot data. And so that's really the crux to me about EgoMimic, is that we just propose a way to use both human and robot data as one and the same. And so ultimately, this enabled us to train models that were robust pretty well to visual generalization. We took our robot all across campus and were able to perform these tasks. And even more than that, we even were able to push in-domain performance a little bit by collecting this kind of high quality episodic human data. And so I would argue that we increased the usefulness of human data a little bit, and we made it as something that was not just for higher order semantics, but you could actually use it in conjunction with your robot data to push in-domain performance as well as generalization. And the costs are probably the lowest of anything we've discussed so far, right? You just need to wear a pair of glasses, you can go out and do these things. And it even opens up towards the possibility of people wearing this while they're doing something like their actual job, like a chef cooking a meal. And so I like to think that maybe if human data was here before, with EgoMimic, we made it at least a little bit more useful. And so now here's the question, right? I said, like, should I drop out and start a data collection company? Is it time to just start sending out glasses to people and collect a bunch of the same kind of human data that we were using in EgoMimic, and will that solve robotics? And so I think there's something I want to talk to, that I've been thinking about that I think we should think of before, we go there and jump straight in. So I think we can be really specific about what kind of human data we're talking about. In EgoMimic, we collected human data that looks like this. It was highly episodic and repetitive human data, which was like really kind of favorable to them. But in the real world, we want robots that can do something more like, they're like ultra long horizon tasks where there's like a really, really big, like it's not repetitive. It's one long task in which there's many, many subcomponents in which some of these things might appear, but it's not the same thing over and over again. And so concretely, I want to highlight 3 key reasons that I think we can't just scale up, episodic human data to achieve like, general robot intelligence. I think we're going to need to develop methods and also collect really good data of this more long-term data. So first, there's this distributional mismatch problem. Super lag. First I just want to highlight this distributional gap between episodic data and the data we see in the real world. So episodic data kind of looks like this. It's very spiky categorical sort of distribution where for each task, you're going to collect 100, 1,000 demonstrations. But the real world looks a lot more like this, right? It is way, way smoother. Each individual thing is less frequent, but you have much more coverage. And so within this distribution, like I said, there might exist things that don't even make sense as a task, which is why I haven't really labeled this, but you might have something like approach the sink, right? While you're doing something in a long horizon task, like unloading your dishwasher, you might need to do this important movement, which is critical to completing the task. But like, just imagine tasking someone of collecting 1,000 demonstrations of approach the sink, it doesn't make sense. Or similarly, take out the bowl from the dishwasher and dump out that little bit of extra water that's always on top of it, right? This isn't really a task, and resetting this would be like a nightmare, right? Like, it's not practical to collect in episodic fashion, but these are things that any individual one of these things almost always comes up when you need it. So I think this is really important coverage that we're not going to get from episodic data. So critically, like long horizon data naturally captures these events, whereas episodic data does not. So I think that's one key thing about long horizon data. And similarly, I think even this notion of a task is sort of ill-formed. And so like, I'm thinking at my own work, like when we're trying to come up with tasks, you kind of just sit down and you like just thinking of tasks is actually much harder than it seems. So if you were to start, like maybe you could think that you wanted to collect data for, approach the sink or dumping out the water. But if you want to start thinking of everything in this way, you just need to start enumerating things like turn towards the dishwasher, slide in your cutting board, or lift up the bowl to place the plate underneath. Like thinking of all these things is actually very challenging. So I think it makes more sense to just leverage long horizon data in which these tasks that are not even things that you think of as tasks naturally emerge. And then finally, there's this issue on diversity, right? If you collect episodic data alone, you can maybe collect something like 100 demos across 5 scenes, and that broadens your diversity. But what's much more efficient is if you collected one demo across 500 scenes, if diversity is your goal. So basically, the point I'm trying to make is that long horizon data is just gonna gives you more diversity, it gives you more. There's things that it captures that episodic data just naturally can't, and so I think we're gonna really need to leverage both of these and develop methods that can leverage long horizon data as well. And so putting it like what I kind of see as the future here is I think we should start to capture people doing long horizon tasks, but not just sending people out into the world just to do whatever, like capturing people going about their day. I think the best way to do this is to capture people while they're actively producing value, right? Someone who's at their job, doing something that they're being paid for, because that this is kind of a way that what they're doing is actively useful. And like similarly, you could collect like the barista doing their shift, or like a chef actually in the middle of their night of cooking, right? And this is something that's kind of unique to the human data, because you don't want, like, if someone's actively producing value, they're not going to want to use Yumi grippers, right? They're going to want to just wear, like, at best wear a pair of glasses. Maybe you'll pay them a little bit extra to do that. It's a lot more practical. So we can really capture things of producing actual value. And so let's put it all together. Basically, I want to talk about like each of these, data sources and where it kind of fits on this distribution, right? So we said robot teleoperation data, because it's our most expensive. I think it's going to be our most categorically distributed, data. So we're gonna take the robot teleop data and collect however many tasks you can, but it's gonna be pretty spiky. And then the role of this human episodic data, as in like Yumi data, will be not only to just expand the quantities of each of these, but also, expand into some new tasks as well. So it'll definitely broaden the diversity of data, and also increase the quantity for the things that you already collected. But then the super critical thing is that I think this long horizon human data is going to fill in all these gaps, right? And each of these gaps are going to be super critical for doing real tasks. And so now I wanted to highlight a bit of work, because I think this has been sort of the whole data side of the story. There's a side of the story which is algorithms. And so I think really clever algorithms can basically reweight where each of these things are on this graph. And so I want to highlight a recent work from my close collaborator, Ryan Benamia at EGT. And so with EgoBridge, he actually, he had a great observation, which is we looked at the PSNE visualizations of what happens when you co-train these policies on human and robot. And Ryan said, hey, these things have very little overlap, and this doesn't seem right. We hypothesize that a really good latent space for human robot co-training should have 2 things. There should be a high degree of overlap globally between these 2 distributions, and additionally there should be local semantic meaning, right? So 2 points that are close to each other in this latent space, even if one is from human and one is from robot, should have some semantic overlap. And so basically, we formulated this, like these exact requirements as an optimal transport problem. So for those of you who don't know, basically optimal transport is a way to find the least costly way to move probability mass from one distribution to another. And so for us, these two distributions, the source and target, are human and robot. And so roughly you can think of EgoBridge like this. If you have this distribution of latents between your human and robot, we need to formulate this as an optimal transport problem, we need to define two things. One is the cost between points. So the cost between points, we basically define as, and this needs to roughly like capture like the similarity of the trajectories that these came from. So we use the dynamic time warping distance of the underlying trajectories of those data points. Doesn't matter too much, but it's basically to say that it roughly captures that the shape and motion between these two trajectories are very similar. And the distance that we want to minimize is the feature distance, the actual latent representations of these two data points. And so what EgoBridge does when you minimize this optimal transport cost is it brings together the distributions of semantically similar human and robot embeddings. And so that was all talk. Does it actually happen? It does. So you can see that on the left, when you co-train with EgoBridge, not only are the distributions way more overlapping than when you co-train, but what I think is really awesome is that if you can start to inspect the local semantics that we were talking about, you can see points that are similar to each other in latent space, even though one is from human and one is from robot, capture a very similar part of the distribution. In this case, it's both like using your left arm to grab this coffee grinder. And so what we hoped and hypothesized was that if we then start to demonstrate things only in the human distribution and not the robot. So in this case, we collected this task where the human, picked up and put the toy in all of these drawers, but the robot only did it in the bottom 3/4. What we found is that EgoBridge was able to start to generalize to these unseen quadrants much better. And so this is still, not released it, but we'll have a full release of this soon and highlighting a bunch of cool results. Okay, so now to begin to wrap things up. Basically, we thought about a few things. We've thought about data on this axis of usefulness and cost. And then we've also thought about which parts of the real world data distribution each of these modalities might cover. And so now I'd really like to leave you with one thought. I think we're at a really exciting time because there's increasingly cheaper forms of data collection coming out, and we're making them increasingly more useful. So this makes me really hopeful of a future where this cheap data really covers out the distribution of the real world tasks that we care to complete. And I think that's going to be the key towards general intelligence. And that's my talk, everyone. Oh, that's all. Thank you, guys.
We can drop that.
Yeah, not yet.
Not yet. Okay. All right. Cool. Just maybe one question since we're I guess raise hand.
Hey, thank you for the talk. I noticed that in the robot teleop, the most expensive, when you do have the hand grip information that you're actually the robot is mimic. But in this visual base, like low cost, like the long horizon version that you're purely rely on version, would you say it's more helpful also to include motion or like some of the hand gesture information as well?
Yeah, I think it's a good question. I think one thing that I'm seeing like very experimentally is that I think this hand grip action is actually very sensitive, and like small errors in this, can kind of completely mess up a task. So I think if you live in a world where you have a sufficient base of robot data, I actually think it might be sufficient to learn a lot of those things from teleoperation and rely on the human data for, other things like more broad movement. But, with that said, I think, their technology will continue to advance, our algorithms will continue to advance, and I can see a world where doing really, really good hand tracking for, each finger of your hand would enable you to, really nicely control like a whole day. But yeah.
Speaker. All right, so next we'll have James Clark from Meta, at the lab, talking about a very, very new, exciting new piece of device called ARIA Gen 2. So you've seen the Gen 1 be used in almost every single talk in this workshop. So I think the team is going to talk about Gen 2. And don't leave after the talk because they actually brought a device and you'll be able to try it on if you're interested. And note that it's gonna be a break afterwards, so you can stay around to talk to
This
them.
computer.
The entire team, there's one team member. So, yeah. And they are also graciously sponsored the event big award for this workshop. Let's welcome James.
Yeah.
刚才那套基本按照我们来的。Paragraphs 打东西就从那上。
Yeah.
知道。
Okay, so I'm up there, I'm cloning my screen or?
其实可能未来就是这个样子，就是有的时候可能需要一些这个最近就是触这些信息，好像 no one really cares so much about computer vision.
Yeah, stop sharing and go, like, make sure that.
Alright.
Yeah.
That's video.
Not, you have to actually.
This is not good. So this is we can switch to the laptop view, but right now it's only sharing screen.
Okay, can you hear me? All right, so I'm gonna myself. We've got about 20 minutes. I want to get through about 15 minutes of speaking and then we'll do a demo of our HN2 at the end of this and show everybody live how it works. So yeah, hi everybody. I hope you've enjoyed EgoAct so far today. I'm going to give you an overview of Project Aria for those that are new to Project Aria. And I'm also going to give some updates for those that have been using Aria for a while and looking forward to Aria Gen 2. So just to do some introductions, my name is James Ford. I'm a research product manager in Meta Reality Labs Research. And I'm actually joined today by two people who work very closely on Aria. Kieran is over here in the middle and he's going to be helping me do some demoing. And he's a systems architect on Aria, has been working from the very beginning on many aspects of Aria. And also Xiaoqing, who's over here, is a research engineering manager that's been working also from the very beginning in Aria. So keep an eye on us and, approach us with any questions that you have as we go throughout the workshop here. So let's dig in. Just some context setting. I think we had some great presentations that already set a lot of this context. But now over 2 million Ray-Ban Meta glasses have been sold in the world since its debut at the end of 2023. You probably all just saw a recent announcement of Oakley glasses that now have similar capabilities. So with RGB camera, audio interactivity, and seamless connection to Meta AI, we're now watching the world adopt what Meta and the community of egocentric researchers have envisioned for many years. We believe that the evolution of egocentric wearable devices and the growing capabilities of vision language models will transform the way we think of personal computing. It'll become more invisible and help us interface across language boundaries and anticipate information moment. And then we're also at an inflection point in the robotics space, and Simmer gave a great tee up for this frame setting here. Large language models evolved into vision language models. They're now evolving into vision language action models that can perceive the world and act directly from a trained model. And now robotics hardware platforms are becoming more and more affordable, and many people have been involved, for example, just in the vision space are now getting into robotics research, and it's exploding at this time. So what do these areas have in common? Both wearables and humanoid robots perceive the world from their own perspective, and that's what we mean by the egocentric perspective. In order to train these models to operate in the domains where they can offer value to us, they need to be trained with data that represents what we experience. I think Simmer put it really well, that it is most valuable to have training data with experts that are actually operating in their domains of interest. So this is an example of what we mean by egocentric data from what's called the Hot 3D data set. And this is a data set that Meta Reality Labs produced and is open source that you can use right now. And this is egocentric data that captures the wearer's point of view and includes information about their gaze, the position in 3D space, how they interact with the environment using their hands. And really, to put it simply, effective contextual AI systems for wearables and machine learned models for robot operation need egocentric data, and they need a whole lot of it. And we're really exploring the question of how much data is required for training these kinds of models. And as a community, we're trying to solve these things together. This is the mission of Project Aria. We started Project Aria in 2020, and the point is to accelerate machine perception and contextual AI research for both wearables and for robotics. And since then, both we and Meta and the minds in the research community here have used Aria to generate new kinds of egocentric data to train and benchmark state-of-the-art models, and created prototype experiences that show these models operating in real time with some of the streaming capabilities of Aria. And I'll just go through what the glasses are here in some detail. This is now what we're calling Aria Gen 1, and this again was released in 2020. And I'll give you an overview of the device. It's packed with sensors. It has eye tracking cameras. It has computer vision cameras. It has an RGB front-facing high-resolution camera and spatialized audio microphones, and then dual IMU, a barometer, and a magnometer. And over 240 research partners now in 27 countries use nearly 1,000 Aria Gen 1 devices to do egocentric research. And these really are the top computer vision labs, contextual AI researchers, those involved in human-computer interaction and robotics labs worldwide, some of which are here today. And we now count over 340 citations of Project Aria and Aria dataset papers spanning a breadth of publications that focus on many things around vision language, robot training methods like we just saw, and foundation model development. And just earlier this year, we announced Aria Gen 2, and this is our latest hardware I have up here with me, I'll put on in a minute, with a bunch of improvements, and we're working hard to make this available to the community in H1 of 2026. So there will be information about how to apply for Aria Gen 2. We'll start that in detail on H1 of 2026. We're really in an information providing mode right now around Aria Gen 2, but I do have a device that I can wear here that we have enough stock to do just basically internal preparation at this point. And we'll also do a demonstration of it live streaming in a moment. And the reason I'm wearing it here, even though it's not live streaming, is I just want to demonstrate how wearable it is. And it's gotten to the point now where we can fold the temple arms, and it's a really comfortable device to wear for long duration research. So Aria Gen 2 provides a step change in usability and capability for the community in several dimensions. As I mentioned, it's more wearable. There are 8 sizes now that we offer. So this is to really adjust for different human factors. And there are significant upgrades to the sensor suite, and it has on-device real-time machine perception. That's one of really the key updates here. And also audio interactivity, so you can talk to the device and you can receive audio feedback from the device when connected up to different systems that it streams to. So here's an overview of the sensor and connectivity of the device. I'll just point out some interesting things for those that have used Gen 1. We now have a USB-C connector standard for charging. That makes it way more convenient to charge. It has an 8 megapixel RGB camera. That's the Gen 1 has 8 megapixel. That's been upgraded to 12 megapixel now. For Gen 2, it has way better dynamic range than the computer vision cameras. There are 4 computer vision cameras that are now facing way outward and downward. So you have a very broad capturing of your egocentric perspective. And there's now a contact microphone and a stereo speaker to make it possible to have, again, voice interaction and audio interaction with the device. And here's an overview of what I think really shows the high dynamic range of the computer vision cameras. If you look at the RGB camera on the right, as soon as the filament on the light bulb goes bright, it sort of washes out all the detail inside the filament. If you look at the CV camera with the high dynamic range on the left, you can see there's really no washout. You can see the full filament, and you can also make out the detail of the lighting in the background outside, where you have all the leaves. And you can imagine how important this is for things like feature recognition or object detection, for example. And the other major update is if you look at the range of the CV cameras, we have huge overlap, stereo overlap now. So we had 30-degree stereo overlap before, now 80-degree stereo overlap. And that enables some really interesting depth applications. And I'll show an example of that in a moment. So perhaps the biggest change for ARIA Gen 2 is that Meta developed its own specialized coprocessor that runs on the device for real-time, ultra-low power consumption, computation of machine perception signals. So for the computation of these machine perception signals you might be familiar with in Gen 1 running on MPS, they now mostly run on the device. And we can do SLAM, VIO on the device, we can do hand tracking on the device, eye tracking on the device, and it can all run in real time, get streamed in real time, and automatic speech recognition. So that's some overview of the device. Now, how do you get and work with the device? This is where ARIA Research Kit comes in. And we don't just provide the glasses, but we have a whole suite of tools that work with the glasses. And we provide these to qualified partners as an application process. So at a high level, ARIA Research Kit is composed of the ARIA glasses, a mobile companion app that runs on your mobile phone that's kind of like a remote control for the device and configuration tool for the device, and a client SDK that enables you to build basically, an application layer on top of the sensor streams. For example, in EgoMimic, it was used quite extensively in the robot perception side. And then tools for analyzing, processing, and packaging data. And we've observed our community have two primary use cases for ARIA Research Kit. The first is the creation of egocentric data sets. You can think about, like the creation of long time frame data sets that get packaged up and then open source. Great example, EgoAct 4D. Kristen talked about that a little bit before. And another major use case is prototyping, applications that can do live streaming and prototyping. So I'll talk about ARIA Research Kit in the frame of these two major use cases. And let's start with dataset creation. So ARIA Research Kit makes dataset creation straightforward. There are some fundamental capabilities of the device, like watertight calibration across all the sensors. So, you don't have many sensors that you're trying to manually get working together. It's all engineered really well to work out of the box. And easy ways to even align multiple ARIA devices together in time and space. And there are profiles that can easily be configured to dial in the sensor configurations most optimal for your recording. So, of course, we've done a lot of work to get the battery working for long duration recording, but still get to optimize your recording for exactly what it is that you want to do in that application in terms of like the frequency of the sensor application. And then we make our core machine perception algorithms, that's again location, hand, and eye tracking, available as contextual signals, and we make it really easy to load, analyze, prepare, and package your data for model training, benchmarking, and more. So even now with ARIA Gen 1, we provide online RGB camera calibration, and this enables near pixel perfect projection of masks back into the RGB camera frame. And that's crucial for sensitive applications like 3D scene reconstruction. This is a Gaussian splatting example of a 3D scene reconstruction. This is not the RGB video, this is the reconstruction live. And what you'll see is this yellow sort of like window washer going across the screen, and this is showing with and without the online RGB camera calibration, just to indicate how detailed and precise you can get with features in a reconstruction if you have really, really good online calibration. And then the other thing I mentioned again is device time alignment. If you have a multi-view sort of application, or maybe you can imagine you have multi-robot application, or even multiple human demonstrators trying to capture the scene, in ways to make it really easy to time align multiple ARIA devices. And that's shown here. If you try to do this manually, when you really get down to zooming in time and space, you can see that things can get sloppy, and this does have an effect when you're working on trying to do things like reconstructions for multi-view. So we have ways to make it like millisecond level accurate time alignment. And for those that have used Gen 1, you may have noticed like a bluish tone in some of the early recordings. We've now done a lot of color correction to those recordings. You can post-process existing recordings you might have. You can de-vignette the image as well with tooling, and this is a comparison to a DSLR camera capture reference. So you've seen the amazing sensor suite. Again, even with the battery that we provide on the device, it's good to use profiles to dial in exactly what sensor you want to use, at what frame rate you want to have the sensor capture, and then with Gen 2, at what frequency you want the machine perception signals captured. And you can do that in the app. So I'll talk about the machine perception signals. We have hand tracking and eye gaze. You can consider these the human-centric signals. And really new, even for ARIA Gen 1, we have 21 key point output now for those that want to do things with like dexterous hand. So really encourage people to try this if you already have ARIA Gen 1. And we also compute the trajectory of the glasses in 3D space. And starting in Gen 2, again, we do this live on the device. So this is a really interesting example of us doing a human pose, live human pose prediction from just the position of the hands and the position of the glasses in space. Some research that we're doing, you can see this kind of thing in a data set called Nymeria. And we, with machine perception services, compute loop closure of the trajectory, and then we also compute a semi-dense point cloud that represents the surrounding space with an extreme level of detail. And what you're seeing here is a city block in Seattle, doing a lap around a city block in Seattle, and the semi-dense points being registered. And yeah, I feel the same. It's very laggy in comparison to what I actually see on my screen. But you can see the level of detail of even the windows on the buildings, I think, is most impressive, up like 9 or 10 stories. Okay, so once you have your data set, if you've done recording, we have ways of making these things really easy to analyze, prepare, and package with Project ARIA tools, and then ARIA training and evaluation kit if you're using PyTorch. And I just want to again highlight some community highlights, data sets here. HD Epic is a data set focused on really, really detailed annotations in a kitchen. EgoLife is a very interesting data set that looks over like long timeframe Q&A. Basically, 6 people got together in Airbnb for a whole week and recording their entire day for the entire time, like swapping out devices every 3 hours. And they do very long timeframe Q&A. EgoMimic, Simmer just talked about that in a whole lot of detail. Really breakthrough work. EgoZero is another one that recently came out from UC Berkeley and NYU. I don't know if they're also in the room. That is working on a different approach using key point basement. So a lot of work coming out using ARIA. We're really proud of our community and the work that everybody's been doing. Okay, so I've covered data set creation. I'm a little sensitive to time here, but I want to talk about prototyping. The SDK is what enables you to take in those sensors and machine perception signals now live with Gen 2, stream them into the SDK in real time, and we'll show a demo of this, and we'll show it. And then, you can also control the device via SDK, and you can stream audio feedback to a user. And now you can, you can do whatever you want on your PC with those streams. Imagine an LLM running on the PC, you can start to have interactivity with that kind of model. So really getting to the world of interactive models. And then here's an example of that. This is actually highlighting, again, the depth capability of Gen 2. Now that we have the 80-degree stereo overlap, we ran NVIDIA's foundation stereo model, which we did some tweaking and optimizing to get it to run real time. But foundation stereo is a breakthrough for depth, and it works really well with ARIA Gen 2. So we have the depth output, and then we fuse this with, this is Connect Fusion, just to show the capability of the depth here. So for everyone that's been asking for a depth camera, a depth sensor directly in ARIA, I think this solves a lot of the problems. So let's jump into a demo live. This is gonna be a little bit interesting for us to set up. Kieran's gonna, I don't know if we need some help switching with them. Kieran's not gonna be on the Zoom. So maybe somebody who is on the Zoom could like point their camera towards him. Might be the best way to do that. Okay. Thanks. Doing our best. I'm worried about how hard the time limit.
That's okay, I mean, it's gonna be great.
Try to get in touch with him and that's the topic. Cool.
We're painting the glasses brown.
You can just double click the.
Point at my
Yeah.
screen. Sorry, this is very. All right, sorry, it's not, the resolutions in here. We can go.
Can you double click on his camera?
Physical zooming. I mean, that's fine, yeah.
You just pick, is it learning to?
We can't, there's no way for us.
Next screen, let me pin down face, yeah.
Yeah, exactly. Yes.
It's not too bad, actually. It's actually okay. It's
Okay, I'll keep my hand steady.
Show the slime cameras. Oh, okay, so maybe I'll talk through this. Here, do you want me to talk through that?
Yeah, sure.
Yeah, okay. So if you look in the top left, this is a 3D view of the glasses and hands and the eye gaze. This like green beam is like the eye gaze vector. And you might see a trace, which is the trajectory being traced in space with extreme accuracy. It's all being live streamed, so it's all being computed on the device and Meta's custom chip that we have. And then what you see on the right is the hands being projected back into the RGB image. And the gaze, the eye gaze, maybe if I hold my hand and look at my hand, you can see
Here. Just go to a different view.
oh yeah, it'll get crop.
Oh,
Yeah.
can you look at somewhere else?
Looking at you.
Okay.
Just conscious all of a sudden.
Cool. And then the other thing to point out, like, go back to the music camera. RGB camera, you'll see that the hand can only be captured up to a certain field of view once you go out to the periphery. But if you look at these bottom cameras, you'll see that the field of view both down and then way out to the side can go like all the way to the periphery and still capture the hands. Maybe a little bit.
So they are views towards the back side.
No.
Oh, I see.
Yeah, they go out and they go down. Oh, pretty wide field of view.
Maybe it's the projector.
Yeah,
Maybe stand a bit away from the projector and then.
sure. Let's see that one's first.
Yeah. And then the last thing probably to notice is that there's this waveform, two audio waveforms. And the one on top, you can see this spiking with my voice, but you don't see it spiking on the contact mic, which is only.
Only if I speak, you'd see some.
Exactly. So we'll talk over each other for a little bit. Kieran will talk as I talk. And then we keep talking over each other. And as you can see, like his voice will only pick up on piece. So that enables us to be like really useful in a super noisy environment to enable audio interaction. Yeah. So that is ARIA Gen 2 in a nutshell. It's also a heart rate monitor. I don't know if we've said it or if anybody wants to see our heart rate.
The foundation
You can come up, you can come up. You can see the screen.
The issue is that I'm a -6 in both
Oh.
eyes. So really, I can't see much.
Can you like very fast move your hand or do some?
You can try it yourself.
They can try it.
There's a little bit of lag.
The
Be due to the
the
frame.
lag just comes from the rendering the display.
I see.
The hands are being tracked at around 30 hertz.
It's all run on your device.
It's all running on the device. So the laptop is only used for visualization purposes here.
How about its occlusion? Like you use one hand.
Right now,
Okay.
I'm very excited to see where it breaks. You just face it. that way, you
Okay,
can see.
okay, yeah. So like this. Okay, this is still good. I cannot see it.
Yeah.
It's good.
Oh,
It's really it's tiny. Okay.
Yeah.
看这个就是
，sorry,
单
good.
的一个步骤。
Just for context, I think the model that we've trained is pretty much what you have in the Quest 3 class devices. So we also know some failure modes where it doesn't work great when you have hand-object interaction. Right, so that's an area of interest for this community. That's something we want to get feedback from and improve the models.
Reframe it.
Oh, visualize it first.
Oh,
A visualizer.
you're running streaming Wi-Fi. Huh?
No, the graphics should screen fine, it's just instead of being very happy or.
That's one try. Oh, sure. No.
Stop streaming this, but you
Got
guys
it.
stop holding my hand.
I went to the dinner. It's been a while.
我以为是10点开始，因为他以为在9点开始。哦，7点半该辛苦了，10点钟我天呀！我真的。
I appreciate it. So I'm a math.
你后面就没他了。
So I'm like, yeah, one of the things is like imagine okay, we like obviously been tracking everything down on the live stream. Required for like a double down. Okay, you talk about like fine tuning.
This one runs eye tracking the glasses at 90 FPS, so it's a more transport. Gives you other signals like the links, like setup units, so you get more 3D information with Android tracking. You can buy right now.
It's a like a series here.
Yeah.
Like one is, I would say right now we are still data bottleneck. There are companies that are kind of popping up that are doing what I'm saying. Okay, how to drop on a certain data collection company. There's things I'm seeing that
I think this tech now,
you don't know. They don't really know yet how to.
Meaning the eye gaze depth.
There's one is I think. Cause like when I look at
Usually for
like some of it is just like not people actually creating value. It's just people kind of going around doing something.
I think I've seen stuff on like Twitter that's just like giving out a bunch of big glasses.
You do the Mad Vision thing, yeah. I talked to them too, and it's like I think they're on the right track, but I think
accuracy.
we're not at the point that like
Outdoors is
I could get like easy hard to measure like that, right? But I want like the density of like good useful information to be really high, because like especially when you change like
research application.
You do really a lot of random things.
But I think it's like I totally agree, you do a lot of random things, but I think the random things you do towards the path of producing value are actually good things. Whereas the random.
For example, like
Yeah, like that's the experience.
Yeah, for live streaming, if you can wait.
that's one thing you need to do.
Yeah.
Sometimes you need to.
Right.
You see some where it's dirty.
Yeah.
It's a little bit dirty, not that dirty. You have to stand in front of it. Here you go. Right, close to one page.
Yeah, and I think this is great. This is actually exactly the data that I wanna capture, right? This is like super useful because like those are the intuitions that you want like to eventually change the budget. And so I think like the bottleneck is that we don't have, we don't take so much to be useful kinds of things. And then also we don't necessarily know like the methods by which we wanna use the data. So like, I think it's open with.
I'm thinking like. What you. I can't do it. Like for example, if you are waitress, like someone call you,
Yeah.
look towards him, right? That behavior is really hard to produce by robots.
We should have robots that people with their head.
Yes, I mean, you can, but I mean, we can have move so close. And also, sometimes they can watch something else. You have something here.
It's absolutely true. I mean, it's not like this is like a big issue though. I think it's just a function of like, it's more, like, 'cause at the end of the day, I'm not like trying to sit and like retarget what someone's doing in one of these videos to our robot, right? Ultimately, I'm gonna ask them data, and a lot of that is gonna be how you actually learn like your base robot, right? The data is not to like, we need to develop methods that the goal is not to just capture like this, then it's like take what's useful from that. I think right now, the most obvious thing that is useful from this really long horizon data is Yeah, great demo. I saw also the video of the CVPR demo. It looks like that one went really well too.
Yeah.
Yeah, it's James's CVPR demo. I think you sent that in the chat for us.
I miss CVPR. so I
Okay,
don't know what
okay.
happened.
It looks amazing. Um,
Yeah.
You should come visit sometime. Or just there.
Yeah,
That's your product hypothesis for what we're building.
really.
So,
Yeah, everything.
Yeah.
About what.
Yeah.
Are you guys thinking about like collecting another data set or like what do you mean from like how would it work from a product point of view?
Yeah. So internally, we have a lot of programs
Yeah.
for contextual AI.
Yeah.
Were you here
You come to Meta.
more of the new classes? They're gonna still be here, so.
Kind of augment their timeline.
Okay.
So we're using this like super memory.
Yeah.
What we are also understanding is like that gives you like a lot of usage pattern.
Yeah.
User education, but the same data is also valuable for.
Imitation learning and reinforcement learning.
People varying data algorithms for data centers.
Yes.
Having cards and those cycles of 4-5 hours. Right, so and it's not like a one task. as you put
Yeah.
it, It's like a. There's a
With
goal.
both imitation and RL fine tuning.
Yes, yes, yes.
Doing this last year or so that they do
When
large scale RGB sim.
that's not the person.
And it to real, but also to RL fine tuning.
Okay.
Yes.
Longitudinal data is very hard.
Yeah.
I'm just curious how you guys.
Yeah. Sure, yeah. Yeah, we should definitely talk more about that. I'm curious to see like what you guys have like, yeah, like what
It's not
data
like human in the loop.
A lot of these things are relevant for the audience, right?
Yeah.
It's like,
right.
We don't have a-
But what are you guys using it for internally?
It is pretty tricky.
Like object detection and all of these things. Okay, yeah.
Until now, what they've done, you can always like go back and like ask questions. They're not very predictive about it.
Okay.
But I'm sure that class of data is also used for reporting.
Yeah, I see. So like right now, I'm just gonna train like a better like, you know, like a lot of the agent, right? For like the
It's your personalized AI,
I
which
see.
knows your history better than any other. Oh, right out.
Makes sense, makes sense.
Just gonna go grab one.
Yeah,
It also works in some ways. I feel like you just move, how do you pull it?
Okay.
Oh, okay. We're actually out tonight. Yeah. Yeah, because I'm here today.
I saw that. That was weird.
It's like in Seattle now.
Yeah. I'm doing, oh, nice. Yeah, I'm doing the internship for 3 months, Simon. Yes. Yes, either on the workshop website or just go to tinyurl.com/egoact. Whoever comes first, but you guys, you can go next. Oh, yeah, let's go.
15 or not. If we're not doing that.
Sure. You guys can go third then.
Okay, sure. Yeah.
Yeah, you were saying.
Have you 3 minutes we can talk?
Yeah.
Yeah, I think so.
With large enough sim environments that are
Anytime.
in parallel, you can get the RL fine tuning to be stable enough so that you can take some imitation policy and improvement. So basically, what I'm doing right now is helping build a simulator that's diverse enough. Like, AI to Thor, we're now building Mojoko Thor.
Oh, interesting.
I mean, if you what you wanted to know.
Shall I wait for 2 more minutes and let's? We'll start? Yeah. Okay, perfect. Then in the interest of time, let's continue with the spotlight session. We have 4 spotlights, and to start with, we'll start with XSIM. Our first spotlight, you guys.
Okay, all right, let's get started. Okay, Teleoperating robots does not scale. It is slow, tedious, and frankly annoying. But human videos are everywhere, and all of us are interested in this question: how to train robot policies from human videos. I think the biggest question here, or one of the biggest questions here, is how do we fundamentally extract actions from these actionless human videos? And one normal approach that you see also is this approach of hand motion retargeting. Take some human video, see what hand motion the robot human is doing, retarget it into the robot's configuration using IK, and replay it. It also can work for parallel geographers like you see here. But you will notice that these videos require slow, unnatural demonstrations. In the first demo, the left hand is always up actually, because the hand tracking method fails if the left hand has occlusion. And in the second method, there's a claw gripper pose that the human must always maintain. It's almost as if the human must act like robots. What happens when a human moves naturally? Like picking up a cup with a frontal grasp that's natural to us and putting it on the holder. The thing is, if you just do hand motion retargeting, this frontal grasp is not kinematically feasible for the robot. And this is the weird motion that the robot does when you try it out. It doesn't mean that the robot cannot solve the task. It can do it with the top-down grasp. There is a fundamental mismatch in actions here. But what is matched here is the action outcome measured by the induced object states. And this is not just true for this task. You can see this trend in multiple different tasks, which will show you, like 5 different tasks, 2 different ones. So our key insight is, instead of matching hand trajectories from human videos, can we learn robot actions that match human object states? Fundamentally, this problem is one of trial and error. The robot needs to try out different actions and figure out which leads to the right object motion. And we define an object-centered reward in simulation that's going to measure the distance of the robot trajectory object states and the human object states. The challenge is that doing RL in the real world is not practical. We need to do RL in simulation, and it requires a realistic simulator that mimics the human video. For this, we develop a real-to-sim pipeline. First, we construct a replica of the real environment using 2D Gaussian starting from a video scan. And for the object motion tracking, we use foundation pose on RGBD videos. And the result is we got this photorealistic simulator, which is not only making RL practical, but it's also grounded in the real world human video. And now with the setup, it's amazing. We can run massively parallel RL, GPU acceleration, and quickly learn robot policies in simulation.
Okay, so now we've shown RL and Sim, but we can talk a little bit about real world deployment. So in order to transfer these policies from Sim to real, we choose to distill these behaviors into an image conditioning policy. So what that consists of is we start with the state-based RL policy, which tracks object states and whatnot in simulation. And then we can generate synthetic rollouts of this in simulation, varying things like viewpoint, lighting, environment, and things about the robot and object themselves. So this allows us to compose a synthetic robot data set, which consists of these image action pairs, and then we can use these to train standard behavior building policies that condition on RGB images and output actions. So I guess there's kind of a question though, like after training only in simulation, can we just zero-shot deploy these policies in the real world? And it's pretty cool actually in a lot of these tasks, we do find that training on this photorealistic simulation does transfer really well to the real world. But one thing we did observe is that in some of these tasks that require a little bit more precision, for example, this task of placing the mug on the holder, you'll very closely notice that like the robot just barely missed the holder open. So this hints at a potential sim to real gap due to these visual discrepancies. And in order to address this, we actually propose an online calibration method. What we do is we adapt the visual encoders of the policy online by looking at these real world rollouts, including the failure videos. So what we concretely do is we start with an initial state in the real world and we spawn in the simulation of the same initial state. We roll out this policy in the real world, and this gives us a trajectory of actions and RGB images in the real world. We replay those exact same actions in simulation to get corresponding equivalent environment states. And now with these paired RGB images across domains, we can actually use this to supervise our image encoder online and basically encourage it to minimize the embedding distance between these two, which correspond to the exact same environment states across domains. And this actually helps significantly improve performance in real world. You'll notice like before calibration, doing this like zero-shot deployment is a little bit imprecise. But after calibration, the precision is significantly better. And we also kind of want to go back to like a primary motivating factor for this is we want to assess, is it really worth doing this XM process versus just scaling up robot teleoperation? And what we find is that we can actually match behavior cloning success rates while reducing data collection time by several orders of magnitude using these human videos, which are one, much faster to collect, and two, our XM pipeline and simulation can allow us to get a lot of robust and diverse synthetic data varying all the different factors that we showed, and actually outperform and scale up significantly faster than robot teleop. And finally, this quick summary, what we do, we take a human video, do real to sim, train RL policies to match object states, and then transfer back to the real.
One quick question.
I think the bottleneck of this approach is how to build the simulation environments. And now these tasks are more about rigid objects. What do you think about? Suppose you want to do with claws, fluid. Can you also do the simulation for these tasks?
Yes. And I think there are two parts to the question. One is simulation generation. I think a lot of tools in computer vision are coming up with these very sophisticated methods that can do 3D reconstruction from single images. And the second point is the dynamic simulation of things beyond rigid objects, right? I think, again, computer vision is making great advancements in this. There's like these particle-based methods that can arbitrarily model dynamics. I think they are in their infancy, but I think that's a pathway forward. Yeah.
Okay. Next up is EgoAct.
Yeah. Interesting.
Okay. Sorry about the technical difficulties. My name is Tony, and I'm here to present dexterous human interactions for in the wild robot policies. So I guess we're all pretty familiar with this in this workshop, but we should ask the question, where should we get the data to train robots? So one way, like the previous talk mentioned, is to use robot teleop, which is very high in quality. But collecting teleop data with high diversity is very challenging because the robot and the teleop setup is usually in the lab. So one way to get a lot of diversity is to use these in the wild human videos, which are huge in diversity, but they really lack in the quality of the data, and it's quite hard to use directly in training. So what if we wanted a data source that's both high in quality and diversity? Well, one thing we could do is just take the robots out of the lab, but this is really challenging. So that's why we're introducing DexWild. It's a human hand data collection system for collecting high quality, diverse demonstrations in the wild. DexWild has two parts: a human hand data collection system that's almost 5 times faster than teleop, and a co-training pipeline that combines human and robot data to improve generalization in the wild. So we believe that good data has 3 main traits. It should be diverse, including many objects and environments. It should be high quality, so it's easy to use in training directly. And it should be reusable. We don't want to collect data for any specific robot embodiment. We want it to be usable for robots today and robots in the future. These traits guide our 3 design goals for DexWild. To collect diverse data, we design it to be portable so you can bring it anywhere. To get high quality, we don't make any sacrifices in data fidelity. And to make sure it's reusable, we design our system to be robot agnostic. DexWild is extremely easy to bring anywhere and collect data. There are only 3 parts: a tracking camera for wrist tracking, a hand sensor system for collecting observations and hand poses, and a mini PC for recording all of the data that you collect. In total, we collect 9,290 demos in 93 unique environments. We collect data at home, at the office, in the kitchen, in the game room, indoors, outdoors, in the day, and in the night. We really brought DexWild to all the different places that you can think of, and we have a huge diversity of environments, objects, and tasks. Even though DexWild is extremely portable, we don't make any sacrifices in data fidelity. We start with mocap gloves for precise hand pose estimation and makes it extremely robust to visual occlusion during manipulation. Then we use palm-mounted cameras to capture high-quality, task-centric observations. And lastly, we use Aruco markers to robustly track 6D wrist pose, which avoids some of the issues when you use other tracking methods such as SLAM. We also carefully design the observation and action spaces so that DexWild is robot agnostic. We begin by mirroring the wrist camera setup on our robot hands. What this does is it aligns the observation space between humans and robots. As you can tell, there's very little difference between the observations between the human and robots. Then we use a robust retargeting method to retarget our human hands to any robot hand that you can think of, even ones that don't exist today. This means that DexWild data can continue to be used as hardware improves over time. So once we collect the data, how do we use it? We choose to use a co-training approach. The human data gives us diversity and affordances about how to manipulate different objects, and the robot data provides grounding and control. By combining them together, we get robust, generalizable policies. So we collect lots of human demonstrations and a small amount of robot demos, and we combine them together in one data set. Then we sample from this data set using a fixed co-training ratio of human to robot data and train standard behavioral cloning using either ACT or diffusion policy. So once we've trained this policy, let's bring our robot into the wild. We showed zero-shot generalization for 5 tasks in 53 environments. And we showed that our policies work 3.8 times better than training with robot data only. DexWild also works for more complex bimanual tasks. And we show that our method enables robots to complete tasks that require coordination between both hands. We also show that if you collect data on certain low-level robot skills, such as grabbing a bottle, we can transfer that to a different task just by collecting more human data and using the same robot data. For example, we collected only robot data for spraying and human data for pouring, and combining them together enables pouring in all these different unseen environments. We also show that since our cameras are mounted on the wrist, if we mount the hand on an entirely new robot arm, we can zero-shot deploy our policies in new scenes. And for a different hand, we show that if you collect a few demos in the lab and combine it with the data set that you already have and co-train them together, you're able to diffuse-shot to new hands in completely novel and unseen environments. If you're interested in checking out our work, all the hardware, code, and training is open sourced, and I'm happy to chat after as well, if you're interested. Yeah, thank you.
Your data set, does it include, for example, the ground truth of your joint on a shooter or the elbow? Or
Great. Hi, everyone. I'm Daniel, and I'm very happy to present this on behalf of my colleagues that couldn't make it. We're talking about articulated object estimation in the wild. Articulated objects such as cabinet doors and kitchen drawers are commonplace and essential in human environment. Thus, we are looking towards building robotic home assistants. We need to enable these assistants to perceive and manipulate these objects autonomously. Previous works have shown that manipulating articulated objects reliably is feasible if the parameters of the articulation are known.
There's also been a line of works detecting articulated objects and their parameters from data. However, such works typically operate on isolated object instances with very good observability of the object. But what if we want a robot to learn about articulated objects in its surrounding from careful observations of other human agents, or from easy to collect demonstration videos, observations made in the wild, if you will? In this work, we address this problem by introducing RTPoint, a training-free approach for detecting articulated object interactions of human demonstrators. RTPoint uses any point tracking to extract the motion of the interaction and determines the articulation's parameters as well as its location in space, given camera odometry. Our RTPoint approach uses RGBD observations and optional camera odometry. It exploits an interaction prior, which assumes that any meaningful interaction is performed by hand. The approach works in 4 stages. The first stage extracts potential interaction segments by using a hand detector to determine when a hand is visible in the RGB stream. As such, detections are noisy. The detection is smoothed and poorly to mitigate the impact of false positives or false negative detections. The second stage processes an interaction segment. Given the segmentation masked by our hand detector, we sampled query points for a class agnostic segmentation model around the Hans mask. The masks yielded by this model identify potential candidate objects that might be manipulated by the hand. On each mask, we extract GFTT key points, which are then tracked in 2D. In the third stage, these 2D trajectories are lifted to 3D using depth channel of our input data, and transformed to a global frame using camera odometry. In this global frame, we can easily filter static points. We filtered the remaining dynamic points for their reliability and smooth the remaining point trajectories to obtain a tight, low jerk path for each point. Using these smooth paths in the fourth and last stage, we extract the articulation model best fitting the motion. For this, we use a factor graph approach, which can smoothly optimize for different types of articulations, given the relative motion of 2 SE3 frames. To obtain these frames from our point paths, we first optimize for the relative transformations between consecutive point cloud observations. To mitigate noise in our observations, we constrain this optimization to using the same base SE3 transform for all time steps, only differentiated by a scaling parameter. From the resulting trajectory of poses, we can estimate the articulation parameters. To evaluate our approach's competence in the wild articulated object detection and estimation, we introduced the RT4D dataset. This dataset consists of 45 egocentric RGBD sequences across 4 distinct scenes, featuring 411 human object interactions. The dataset provides ground truth labels for all interactions as SE3 twists, as well as the labels easy and hard regarding the observability of the interactions. As the camera is moving in the wild setting, we also include centimeter accurate ground truth camera trajectories. We compare RTPoint to 2 deep learning-based baselines and 2 classical approaches. We find that RTPoint yields the lowest prediction error for articulation parameters for both prismatic and revolute joints, which is true overall, but also across the easy and hard categories. In the ablation, we also determined that both our point tracking and the articulation bias trajectory estimation are major contributors to RTPoint's accuracy. A qualitative analysis of the inferred articulations confirms the quantitative results. Overall, we see a reliable inference of the articulation axis and its location, though occasionally the location for axis of rotation can deviate in harder cases. For a more detailed description of our method and a more thorough breakdown, I refer to the full paper and or the poster. And you're very welcome to also reach out to my co-authors for more detailed questions. Thank you. Any questions?
Thank you, Daniel. Let's continue with the rest of the session. We have two more speakers now. We talk to talk, and then we will have the lecture to talk. All right. I'd love to invite Amanda. We'll have a minute. Amanda recently started as a research scientist at Meta. He completed his CSG from the robotic and advised by
刚才会走马观花的，没有看的这么
robot learning from videos, robot learning from human videos, and so on. So we're excited to see what he's come up with. Thank you.
刚才都讲了一遍。
Yeah, let's get started. Yeah, so the work I'll present here was mostly done in CMU, although I'm a research scientist at Meta now. To begin with, let's take a moment to imagine what the future looks like. You're happily watching TV, sitting on your couch, and you suddenly crave some coffee. You think about coffee and you press a button on your couch, and the very nice robot in your kitchen makes you a nice cup of cappuccino and brings it over. So everything is going great, but just as you were about to grasp the cup of cappuccino, you suddenly drop it on the floor and coffee spills all over. But there's no cause to worry because the robot in your kitchen has you covered. It quickly comes up and cleans up the floor and makes it sparkling new. Now, all this while you are still on the couch, happily watching TV. Now, this future is great, and I'd certainly like for this future to be true. But one might argue that this future is sort of already here. We do have robots that can clean the floor for us, like the Roomba on the left, and we have robots that can make coffee for us, like this Artly coffee robot on the right. Now, these systems are great and very reliable, and hence they're in deployment, but they do come with significant limitations. So each of these robots are catered to just doing one particular task, either cleaning the floor or making coffee for you, and also require the relative workspace to be somewhat structured. So we're still far away from this future I just described, and to really get there, we would want robots that can perform not just one task, but multiple tasks, and do them not in structured environments, but in very natural scenarios like in homes, offices, and kitchens. Now, here are just some examples of scenarios like these where humans effortlessly perform a lot of different tasks. And in this talk, I'll show you how we can get robots to perform tasks in these very natural environments. So all of these executions will be with policies that can perform multiple tasks and not just one task. And the user, the human, just gives a high-level specification like a language instruction to perform these tasks. To set the stage for the talk, let's look at the overall framework. We want to train a robotic policy that can execute actions in an unseen scenario, where the user just provides some high-level goal in the form of an image, language instruction, or a video showing what needs to be done. And this policy should take in that instruction and output actions in the environment such that the task is performed. And all of this should ideally be without any test time adaptation or fine-tuning, where the user just tells the robot what to do and the robot just does it. So before I dive deeper into my work, I want to contextualize how prior works sort of stack up against this goal. So the very prominent line of recent work is end-to-end imitation learning. And the idea is not new, it goes back to decades, but the reincarnation of this with modern deep learning approaches is kind of interesting. The idea is to collect sort of robot teleop data by holding the joystick, or even by maybe holding the robot itself, a bunch of different ways. But the idea is to show on the robot what can be done. And then once you collect a bunch of data, you can train a policy to output robot actions conditioned on the previous observations. perhaps this sort of single task setting is not as interesting, but recent works have made this very framework goal condition. So instead of collecting data for just one task, you collect data for multiple tasks and you train one policy conditioned on a goal, which typically is a language instruction. And this has recently caught the attention of industry quite a bit, and billion-dollar startups have been funded based on this very simple recipe of collecting lots of robot teleop data and training very large models to fit on this data. And if you have been following the success of deep learning, this shouldn't be very surprising. To quote Ilya, success is the only possible outcome if you train large models on domain-specific data that you acquire sort of in a large scale. However, the results from many of these approaches don't really scale to in the wild settings, and they're somewhat still limited to sort of tabletop manipulation. And the reason being that it is hard to collect robot teleoperation data in diverse natural scenarios. And just to put into perspective some of the more impressive results from startups in this space, for example, this video from Pi here, it required thousands of demonstrations for this particular task in order to do it well. And so although you have trained a general model, you are sort of using lots of data for a particular task, and the model can only do that task. So to rephrase Ilya's quote, success is the only possible outcome for tasks that are within the data distribution. And hence the natural question becomes, how do we expand this data distribution without requiring lots of teleoperated robot data collection? And that's exactly what my research is about. So I'll show in this talk how we can leverage lots of human video interactions that naturally exist on the web that you don't need to collect yourself, and primarily do third-person learning, where you observe human videos and learn to predict actions based on that by using only a limited amount of robot interaction data. And these web videos of humans are sort of in natural environments, and they correspond to a lot of diverse tasks. So this is exactly the setting we want robots to be deployed in. And this framework shouldn't come as a surprise, because as humans, we do this kind of observational learning all the time. We watch others observe, others do things and learn by observation, instead of someone holding our hands and showing how different things need to be done. So this is very intuitive for humans. Let's make it more intuitive for robots as well. Now, these human videos provide a lot of different cues. For example, a video of a person pouring from a cup, you can get high-level cues about how to approach the cup like a human would. And you also get low-level motion cues about how exactly to grasp it and how to pour from it. So these web videos are useful at different levels of abstraction. And we'll look at how we can learn to extract and predict all of these. So the key challenge then becomes, as has been mentioned by some talks in this workshop as well, how can we extract actions from these human videos, because they don't directly give us robot actions. So to tackle this key challenge, my research has factorized the overall policy learning problem into two parts. The first part is a visual interaction plan that predicts how a human will do a particular task in a particular scene. And this is somewhat embodiment agnostic, not necessarily limited to a human doing a task. It could be a sort of a general task agnostic representation of how the manipulation should happen. And once we can train this model from lots of web videos, we need to solve a much simpler problem of grounding that prediction in robots' actions. So to do that, we typically collect a small amount of robot teleoperation data and train a policy conditioned on the interaction plan to output robot actions. So that's sort of the high-level picture. And I'll try to dive into a few of the specifics of what are the visual interaction plans first. So early in my PhD, I looked at how we can do hand-object prediction, where you predict how a human hand should manipulate an object across time. So given a scene and some goal, you predict how the human hand should evolve in the future, how the human hand and the object pose should evolve in the future. And more recently, I have shown how we can get these more embodiment-agnostic point tracks to work. So the idea is the same. Given a scene and a goal, you predict how point tracks in the scene should move in order to realize this goal. Here you can see the point tracks correspond to the points in the book moving towards the camera, and that is what's being shown by the goal image here. And very recently, I've shown how we can get video generation models to generate interaction plans. Here, the interaction plan is literally a video of a person doing a particular task. And this is by prompting a video generation model that's conditioned on text and image, zero shot. So I'm not fine-tuning or messing with the video model in any way. Let's dive a bit deeper into this embodiment agnostic point track plan. So to get data for training such a predictive model to do future track prediction, we use lots of web videos and run off-the-shelf point tracking on them. And such computer vision approaches have become really good recently, Co-Tracker and so on. And this is sort of a very standard computer vision problem. So this gives us the ground truth for training this prediction model. And for training the robot execution part, we just require teleoperation data of a broad set of tasks. And the order of magnitude of that data set would be much less than the amount of data we use for this first part. So the prediction model is very simple. Given initial image and goal image, we want to predict how points in the scene should move without having access to the underlying video. And we can train this from lots of internet videos and deploy it directly in a robot's context. So in front of a robot, we have the image of a scene and we have depth. So we have 3D points in a robot scene. And this model gives us the 2D projection of those points in subsequent frames. So that lets us extract some rigid transforms of how the object should move at each time step. That's a very high-level open loop plan that you can obtain just by training this predictive model in internet videos and rolling it out on the robot. And once we have some limited teleoperation data collected on the robot, we can train a residual policy to output actions such that the open loop predictions are corrected at each time step. So this is sort of the high-level idea. I don't have time to go into all the details, but happy to talk about it offline. What this gives us is a single policy that can be goal conditioned for a wide set of tasks. Here are deployments of this policy on the Spot robot across natural kitchen scenarios in Pittsburgh, where you can see you can do all kinds of tasks from pouring objects to articulated object manipulation, picking and placing, and so on. And all of this is possible because we are learning this very general embodiment agnostic point track prediction model from lots of web videos. Here's just a glimpse of what this looks like. These are all zero-shot executions. We move the robot to a natural scenario, ask it to manipulate a particular object based on the goal shown on the top right, and the robot just does it in one shot. So I'll sort of cut this video short and move on. Since we released this work in ECCV last year, this idea has been picked up by the community quite a bit, and there have been lots of point track-based works doing all kinds of tasks, from web videos, from human videos, from all sorts of other domains. So this has really been impactful, and I'm glad because I do think this point track representation is a very natural and intuitive way for capturing how object manipulation should happen in a scene. For hands, you already know we have accurate sort of meshes, but for objects, it's challenging. And this is sort of a very nice and intuitive way to go about it. And here are some results for what the predictions look like. So given a scene and a goal, we predict point tracks by rolling out the model zero shot, and we have the robot execution condition on the point tracks. And the reason this works for object types that are outside the robot interaction data is because the first part generalizes. It's trained on lots of web videos. It has sort of seen everything. And the second part of converting the interaction plan to robot action is a much simpler model, much simpler problem because we already have the approximate interaction chalked out. And this works for other tasks like pouring, picking and placing objects, and opening doors. So all of these are executions with a single policy instead of having separate task-specific policies. Now let's look a bit deeper into the video generation-based interaction plan. So here the idea is to generate a video of a person doing a task, given an image of a scene and a language description telling what needs to be done. And the reason for looking at video generation is that video models are only getting better. Here are just some examples of what video generation looks like for Google and Genmo Mochi. These are already outdated and current results are even better. So if we can use these video models trained by sort of the wider community, since there's widespread interest outside robotics, that's a big win for robotics if we can use them zero shot. So that's the overall idea of this work. And the video model we used here is already very old. It's Video Poet from ICML 2024. But you can see that the generations are plausible. They respect sort of some notion of physics, although the quality is not that great. So it follows the prompt instruction, it doesn't generate weird artifacts and so on. So that's the video model we work with, and we roll it out zero shot in a scenario. The nice property of this is that we can also do point track extraction by running the tracker on top of the generated video. So we can also get all the benefits from the previous work for free once you can generate a video in a new scene. So the approach is fairly simple. We first teleoperate the robot to collect a bunch of data. And for each of the robot demonstrations, we also generate a video of a human doing a task. So we sort of get this free paired data, right? Without actually having a human do the same task in the same scene, we can generate a video of a human doing a task by rolling out the model from the same camera as the robot. So that's the idea of getting this offline data set of robot interactions and paired generated human video. And the model will first sort of extract point tracks. This helps in capturing motion explicitly because the generated video might have some artifacts, and we don't want the policy to over-index on those artifacts. So once you do this point track extraction, the policy is fairly simple. It conditions on the generated video. It uses the point tracks for defining some auxiliary loss and outputs robot actions. So all of this complex machinery is just for training, but for evaluation, it's again very simple. We have a policy that we can query with a language instruction. We move the robot to a new scenario and ask it to manipulate sort of a particular object based on language instruction. So it first generates a video of a human doing a task, because this task is sort of maybe out of distribution for what was in the tally of data. But since the policy has learned how to associate a generated human video to robot actions, it can perform this new task fairly reliably. And we just repeat this at each time step, similar to standard model predictive control, and that's how we go about it. As I already mentioned, the video model is Video Poet from Google, and current video models are way better already. And we're using this video model zero shot, so you can plug in a new video model in this framework and it'll still work, keeping everything else the same. And just for context, the video model was trained on 270 million web videos, and the robot interaction data was just 100,000 trajectories. So this is, again, giving an idea of the scale of web video data that we can use for robotics, especially in a framework like this, where someone else is doing the heavy lifting of video generation for us. And we just need to collect significant orders of magnitude less robot interaction data. Now, here are some qualitative results of what this looks like. This is motion generalization. So we don't have a motion of the type pouring in the robot interaction data. We first need to generate a human video. And since the generated video is plausible and the model has already learned how to associate a generated video with robot actions, it can perform this new skill that it has not seen in its own interaction data. Then we have the results for motion type generalization, wiping the table, where again, we can see that this new skill can be solved by the robot. And we can also do chaining for long horizon activities. So all of this was single task manipulation, but because this framework just requires language as an input, to perform a long horizon sequence, I just ask Gemini, what are the steps involved in this long horizon sequence of activity? Gemini gives me some subtasks, and we do human video generation for each task, followed by robot execution, followed by human video generation, and so on. So this gives a sense of how we can use this model that was trained only for short horizon activities for doing long horizon manipulation, just by doing this inference at test time, using sort of the power of pre-trained language models. Okay, and here are some success rate results compared to end-to-end imitation learning that doesn't really perform well for higher levels of generalization, and imitation learning with just predicting a goal instead of a video. This approach that predicts human video for the entire task really outperforms all of these prior works. And this should not be very surprising, because the video model essentially captures a lot of world knowledge, not just in terms of representations, but also in terms of motion. And we're really using that as much as possible to get these higher success rates. And here's a glimpse of the overall results for this Gen2X policy. These are, again, all results with a single policy that's queried with different language instructions by users. These are in natural scenarios in Mountain View. Okay. I'll sort of cut that video short and move on. So far what I've talked about are this coarse manipulation for daily activities, where we can learn to predict motion in different forms, in the form of hand trajectories, in the form of point tracks, in the form of a generated video, and do sort of coarse manipulation tasks like pouring, scooping, picking and placing objects, articulate object manipulation, and so on. And this framework of factorizing the policy into two parts has really helped in this setting, because you can learn the first part from lots of web data. In the next few minutes, I want to focus on how we can go beyond coarse manipulation and do more dexterous manipulation in the wild. This framework, again, is sort of intuitive, and the question that I want to ask is, can you predict richer motion cues from web videos? So going beyond these sort of 2D point track predictions, given similar videos, web videos that are RGB, can you predict more explicit representations like 3D meshes of the hands and the objects interacting in the scene? Now, these predictive models have also become really good recently, thanks to the computer vision community. And the question here really is, how do we predict these in the future instead of just reconstructing them? So here's some very preliminary work called Web to Grasp, where we showed how we can get this sort of dexterous grasping in the form of functional grasp, where an object needs to be grasped based on the purpose of it, working by just doing hand object reconstruction from these web videos. the overall idea is fairly simple. Given these web images, we're not even looking at videos here, reconstruct the hand mesh and the object mesh, retarget the human hand to the robot hand. This is sort of kinematic retargeting because you already know the meshes. And you align the object mesh with sort of a ground truth mesh. So here the ground truth mesh is not obtained from a CAD model or anything, it's just obtained from a text to 3D model. So given this image and the language description of the object, you feed it to a text to 3D model, it gives you a mesh. You align the mesh you have inferred in the object with that ground truth mesh. That gives you the pose of the object in the image. And then you have a retargeting of the human hand or robot hand that you can use to infer this functional grasp. So I'd invite you to check out this paper for more details. But what it gives us at the end of the day is training data for training a policy. And eventually, by using these lots of web images, we can train policies to predict grasps given a mesh of the object. And that is what this DRO model is. This is a prior work from NUS that we use. And we can execute this in simulation. When you execute in simulation, there will be some failed grasps. And that is fine because you can infer that accurately in simulation. We reject them and expand our data set in simulation just by rolling out this model that we have trained from just web images. And eventually we can get a good set of samples in simulation and then roll that out zero shot sim to real. So there is like almost no sim to real gap here because we have obtained the mesh reliably from web images. So here are just some examples of success cases and failure cases where you can see the diversity of these grasps across a lot of different objects. And here is what the results look like of functional grasping in simulation. So these are rollouts from the policy in the case of all of these different object types. And you can see it works fairly well across a broad set of diverse objects. And here are some results for real world manipulation, where again, we are just doing grasping. So the robot needs to go to a grasp pose and execute the grasp. And here also you can see that this policy sort of generalizes really well to all of these different object types. So this is just preliminary work in doing functional grasp predictions from images that are web images of hand-object interactions without using any teleoperation and without using any sort of supervision beyond just images or hand-object interactions. So quickly in the next 1 or 2 minutes, I want to sort of talk a bit more about beyond robotics. So all of these predictive models are really useful for robotics, as we have seen. But going beyond that, it can also be useful for humans to perform new tasks in new scenarios. For example, cooking a new dish or assembling new furniture. We have all of these predictive models that can be deployed on, for example, these Meta Ray-Ban glasses, right? And if you can load these predictive models on these glasses, they can give us information of how a human should perform a new task in a new scene. Now, this has probably been talked in this workshop already. So I just want to highlight some recent work we had along these lines where we are doing hand trajectory prediction. These are 2D predictions of the wrist. And we trained this model again from lots of web videos. We didn't deploy it on the glasses yet, but I guess that's sort of a very intuitive next step. So these predictive models can be helpful beyond robotics. And that's kind of exciting because they're really powerful in forecasting how actions should happen in new scenarios. Now with that, I'll sort of summarize my talk by saying that we have shown how we can extract lots of motion cues from web videos and learn to predict these motion cues in new scenarios. And all of that has given us the ability of acting in new scenarios based on these multiple different robotic embodiments. With that, I'd like to thank my collaborators, and I'll be happy to take questions if there is time. Thank you.
Time for maybe one question. Yeah.
Thanks, Abhanga, for the great talk. You showed a bunch of works going from high-level extraction of plants to low-level. As we go more and more low-level, do you think it's better to make our robots more dexterous like humans, or there should also be focus on making embodiment transfer algorithms better suited for embodiment transfer? What are your thoughts on that?
Yeah, I think both are important, but I do think that currently robotic hands are good enough that we can actually try to deploy all of these on the current hands. So hardware currently is not like a big bottleneck for deploying all of these policies on real hardware. So I think that's like a reason people probably give, right? That hardware is not there yet, but I do think it's there yet. We just need to develop the right policies for that. But of course, if we have better hardware that are more human-like, then some of these problems will be solved on their own.
Final speaker here today, we have Salomon.
Let's see.
Yeah, you can share it. So Jala Wong is an associate professor at UC San Diego in the EC department. He is also a member of the robotics team at the TLOS NSF AI Institute. He was a postdoc at UC Berkeley with Alexei Efros and Trevor Darrell, and he received a PhD in robotics from CMU, where he worked with Abhinav Gupta. He's been working on several works on robot learning, from humanoids to learning from videos and so on, and we're excited to
Do we need to return to function? Will you turn it on?
No, you don't.
Okay. All right. Hi, once, was three. Hi, thank you for coming to the talk. It's already lunch almost. So I'm Xiaolong. I'm from UCSD. I wake up very early in the morning today. So come with students, I think, all the way down. So I'm presenting this humanoid policy as human policy. So this is actually the title of the paper. This can be referenced by Google Scholar, experimenting. So this all starts from this teleoperation thing that we did a while ago. So you use a vision flow to control humanoid robot doing something. And we did a very little Q system in here that, so this very Q head here can actually move along with the IMU sensor that is inside this vision probe. And then it kind of streams what this camera sees, right? So it sees the back student and then it streams to the VR. So you basically see what the robot see. So this allows us to do some very remote teleoperation, right? So this is videos that actually shoot it. This is Ge Yang. So he's a postdoc from MIT. Then he's able to carry out the robot that is in UCSD away, very, very far away across the country. And then after you collect the data, you can do some imitation learning and do this CAN insertion task. We didn't exploit too much on like diverse data. It's just inserting this particular CAN. And I really like about the videos in here, the part, especially like this video, Egocentric video. It really reminds me a lot of Ego videos you guys show as well. Ego 4D or Ego like Epic Kitchen. It's really just the difference is not human hand, it's the robot hand, right? And another thing I like about this work, we also predict the camera position. So essentially your head is how your head is moving. It's also one of the action items in the policy. I also want to show this particular video because in the lab we have 3 teleop projects that in parallel because we have a lot of people. And only this system can do this task is because when you're doing teleoperations, if you're seeing from the first person view, it's actually incredibly challenging to do this task. You do need to, the teleoperator do need to look into the first person view, to look at the small thing, and only then you can pick up the small things. So it's not that easy for this task. But overall, like everyone mentioned, teleoperations are very painful things to do. And because if you remember the first video I just showed, right? So it's essentially when you're doing teleoperation, the humans and the robot are almost doing the same motion. How the human do things and how the robot do things in teleoperation is really just a 3D transformation plate. And the views are always also very aligned. So that's why we start this work, like try to do co-training with human data and robot data. So the human data and robot data is very similar, as I mentioned before. And I think that our people stream is basically you can train from internet videos, right? So YouTube videos. But the fact is that YouTube videos are full of interesting videos. There's not enough boring videos, dog cat videos, for example. So it's actually very hard to find videos online that is useful for the task. Actually, we already actually talked about this like 10 years ago when we were doing the Sherry data set with Gupta. We do collecting egocentric videos and first-person video from homes to old times. But essentially, we want to have data collected for task oriented, right? So it's not just random internet people data, more task oriented. So this is work actually sort of collaborated with Apple. So you all see the EgoDAX, so I don't need to explain that much. It's actually a little bit before EgoDAX that we can actually collect 28,000 demonstrations, which you have a lot more there now. But this is like 2 weeks of work. And then if you do like humanoid robot demonstrations, 1,000 demonstrations maybe takes almost a month for 1 or 2 students to do the data collection. So much faster and scalable. And we are collecting data that is just doing these are the tasks that is going to be done exactly the same task that the humanoid robot is going to do. Right. So yeah. So this is just showing that you can actually collect very diverse scenario in different backgrounds. So that's the good thing about it. Collecting egocentric videos, like everyone mentioned. And then the device we're using is using Vision Pro. If you are rich and you have more than 100 people company, then you can purchase enterprise license for Vision Pro. Then you can use this main camera. If you are poor alias like India, all you can do is like hanging a Z camera on top of the Vision Pro. We are not qualified to have their access. So basically there are 2 settings in here in the lab. We're basically doing the hanging a camera on top of the camera. But the good thing is that it's really overall it's good that so you can collect human data and robot data. They're very aligned. So what I want to show is also showing the EgoDAX is that it's really providing very good tempos when you are collecting the data with Vision Pro. And in general, maybe there are meta people in here. So in general, it's still doing a little bit better than Quest, I would say. Let you guys compete. But so I think the Vision Pro offers very good posts. That's very important for our algorithm, right? So the algorithm side, that what we really do that I find it's very interesting is that we are not training a humanoid policy. Actually, we are not training a robot policy. The whole core thing that we try to do is we are actually trying to train a human policy. Right, so our language is trying to predict what the human is going to do. So essentially, the inputs are all converted into the human representations. So if you have a humanoid whatever demonstrations, you are not converting to all the joint positions of the. You're not the input of the language is not the joint positions of the lecture's head. It's actually you do forward kinematics to convert it back into the 3D human time points, and then also the 6-stop response. Okay, so the input state is actually aligned back into the human space. And then there's another thing. Basically, if you want to do co-training, one thing we do realize, because when we are doing teleoperation, especially with the hands we were using, you need to be very careful. Otherwise, you break the robot very easily. So usually it's very slowly. But when human is doing things, it's going to be very fast. So we just kind of need to slow down doing some video installation to slow the video down. So specifically we slow 4 times down, and it's just some hyperparameter too. Right. So we mix this data together. Just to give you a better idea, what do I mean? So this is basically a 3D hand pose you can give using visual recording, right? But then for the robot side, you can essentially do the same thing. So this is, you get the robot joints, and then you can do form kinematics and convert all the representations back to actually the human hand pose space. So this is actually the pose in human hand space, not in the robot hand space. So essentially you're converting all the input aligned into like more like a human pose representation. But of course, the RGB, you cannot do anything. So when there's a robot data, we have robot RGB, a human hand pose. When you have a human data, you have like the RGB of human data and then also human hand pose, right? So either have this or that. And then you go into these beautiful transformers and then but basically predict what is the next action in human space, okay? So it's actually predicting where the human hand is going in the next time set. It's not robot. And then what you do to convert to a robot action is basically you do inverse kinematics to get the joint, the any factors for the action, how the arm is going to move, and then you do targeting that how time is going to do. So in some way, I would like to phrase it as we are actually training a human teleoperator, right? We are not training a robot policy. We are training the autonomous teleoperator. And then the teleoperator can control what the robot does. The benefit of this is actually, we'll show later as well, that we can do cross embodiment. So essentially, we actually experiment with different humanoid in different places. If you can align all these different robots into all just the human action or human representation space, and then you do different inverse kinematics and all these different retargeting to go back to different robots. So sharing all in the human space, but then when you deploy, you can do different inverse kinematics to get to different human robots. So I will show some results of this later. But the initial thought is actually try to do it cross embodiment. So we have some numbers, but you can just look at the final column. So essentially, adding human data allows you to generalize better, like most of the claims is in this way. So specifically, what does it mean? So it is actually incredibly easy to, when you are doing just robot data training, this is actually happens a lot of time. It's just kind of overfit to some of the data. You cross in the air and then you pretend you are doing things. So some overfitting. And then training together allows you to generalize better. We also have a lot of fun tasks that is not actually useful, but just very useful. To cut left to right, right to left. And the robot data is collected without this random background, but the human data is collected with diverse background. And then we show that people train together and we generalize to more different backgrounds. Right, so some of the pooling. So again, actually the path is not necessary in here. We put these things in here for just easier to compute the accuracy or success rate in general. So the last example that I want to show is basically, we have collaborated at CMU. Guanya is our collaborator in CMU. So we bought our Unity robot very early. So that actually, this arm is actually a 4-dot arm, and then later add the 3-dot in the end. So this arm is actually different from this arm, this purchase later. So it's cross embodiment, different versions of different versions of H1 is cross embodiment. So basically, single legword works on both robots. Right. So I want to go back a little bit actually. So we actually look into this space for a long time. This is my first work in UCSC when I joined. So this is my student user. Everybody here graduated almost. This one is left. So it's actually quite an old work, and that is initially done in 2020. We submitted to computer vision conference. It only get accepted like 2 years of cycle. For vision people, I think the most common we get is just the vision is too easy. Like at the time, actually, what we do is basically we record video like this, and then we do a 3D pose estimation, and then we do retargeting to get robot demonstrations, and then do imitation learning. Right. So vision people will say, why are you recording video in this like this, right? But the fact is that the computer vision still was not working very well, even recording this way. So you see the cup is actually still pose estimation is quite bad. So what happens now? And what happens then, right? So one thing is what we show is tempo is much better now. So that's important to us because we're essentially trying to train the human policy, right? So you need to have accurate human action output. And then pose estimation is still not very good, actually. Even you use a lot of the new big models with slow frame rate now, it's still very challenging because once there's occlusion, there's a lot of ambiguity. But then we now just take in the RGB image, we don't do, because before we're actually doing more like first state estimation and then train policy on the state, estimated state. Now we can train on RGB, so we don't bother anymore. And then you have a better system now, so you can collect actually robot data to do for training. At the time, we were actually just doing only human data to training, and then plus RL. And then you have a better transformer model now. So basically, so you can actually consume data from humans and robot at the same time. So that's also important. Like better self-supervised training network provides better abstraction. So I'm showing this is basically, I feel like I think we are doing something new, but it's maybe also not that new. That a lot of things are actually working now, but not working then is because of these changes. More like the communities has pushing better hand pose, better Blackboard, and better system. So it's more like better system integration overall. And then if we go a little bit a while back even, right? So I talked to some guys in ICRA, so I decided to add this video. So this is in CMU, by the way. So this is one of the work that learning from demonstration. You can see this is spending 1 minute to do segmentation, basically. So you segment the objects and then you can do repeat the motion. So these things are all actually there for a while. So that's the past, right? So looking forward, so I haven't talked about is the sim-to-real thing. So we actually did a lot of sim-to-real work for the past few years. It's just like it never looked as cool as all the fancy teleop. So we also do some teleop. But sim-to-real is always what I have been working on. So we have a paper in here. We haven't released archive yet, but we have a paper in here. Basically, it's trying to generate demonstration in sim and then do sim-to-real transfer. So we have this video in here. I kind of need to play it because the students spend a lot of time to make this video. So it doesn't really say anything. It's just cross-check. But I think it works well on sim-to-real. Basically, this is showing continuous. You just put objects and then you can keep cross-painting different posts. So sim-to-real transfer still works quite well. Yeah, so I think human data is important. Some simulations into real. I still think we can still push that direction. Yeah, that's all. Thank you. Yes.
Yeah, very interesting work, and I think very interesting, exciting now and then. So I have a question in your first videos about like teleoperation from 3,000 miles away. So here, like you teleoperate the whole body or just upper body?
Yeah, that was upper body, but we have whole body as well. I didn't want to show here, but I can show here. So sorry. So we did actually also have that, right? So I actually decided to hide the slides because I see it's coming late. So I last minute I decided to hide these slides, but we have a work in here as well doing both body teleop. Yeah, I think it's an interesting thing because actually it's also from some of discussion in ICRA. We were actually talking about that now you have doing all these hand fancy things, but what about arms? What are the best arms to use on top of hands, right? And then going beyond, how do you kind of further reaching reaching to everywhere? So I think integrate with that like whole body.
Thank you.
Yeah, very nice, very inspiring presentation. I have a lot of question about this, like humanoid data and human data. And one is, like, what's the role of tactile sensing? The second question is, like, I see you use vision to do the like human data collection, right? What are the conclusion? Like, do you need mocap like glove devices? And the third question is, when you do the retargeting, do you need a simulator? Or you just because I feel like some naive, like we don't consider the hand object interaction, the just the hand to hand retargeting sometimes is not that accurate.
Yeah, so to answer the last question first, in case I forgot. So it's only doing the more naive like matching the fingertip rotations right now. So it's the fingertip of human hand and robot hand, they are all touching the same position. So that's what we try to align on. So for that, if you are considering objects when you do retargeting, I think that's a very interesting direction. Actually, the problem of retargeting and policy, like one there is retargeting, one is policy, it's actually not a clear boundary there. If you are doing more smart retargeting, that's almost a grasping policy, right? So at that point, you would think about, I mean, we are think about learning the retargeting as well, but then we find that that's almost just learning the grasping. So I think it's actually not a very clear boundary between retargeting and policy. So yeah, we can talk about that later. What are the first two questions?
The tactile sensing and also the
sensing is and we didn't have tactile in here. I do feel like actually I would say this right now is more mature for a lot of pick and place tasks. I don't know that if it works for more complex interaction tasks. So that's why I don't know. I think if you're doing actually very complex interaction, like again in hand rotation things, the contact of robot hand between robot hand and objects and the contact of between human hand and object actually quite different. So it might not necessarily transfer for the morphology and other context that would be quite different. Yeah. And what's the second?
The I guess motion capture device is the camera good enough?
Right. Yeah, occlusion is okay. I think actually, I mean, if you occlude in a way that is going behind this object, is still try to do a guess of where the finger is. It's not that bad. Right. If you are under the table, then it's no hope.
Thank you. Thank you.
Thanks, okay.
And just the final thing. You have more space.
I think that's
And everyone from do it later or we met at the we work with everyone. Okay.
So you have the Larry school?
Yeah.
We have some work for best paper. We have some Quest 3 headsets. And we also have Ray-Ban medical digital work. That's the only one, yeah. Yeah, exactly.
Okay. Start with the runners up award. So good news to all the spotlight speakers is everyone gets an award. Something. Nobody is going empty handed. So for runners up, we have articulated object estimation in the wild and technical enforcement. Let's come up.
I'm taking a picture. Great, get through this. Come take it from your okay.
Doing the photography.
Oh,
You can choose. Simon is taking a picture. So we can follow.
I want the Ray-Ban.
Yeah, I think
We can take a picture.
Get a bit closer and when this.
Is this the right? The big one?
Yes, yeah, yes.
Alrighty, 3, 2, 1.
And so the best paper award, which will now go to EgoDex and DexFile. The authors can come up. All right, that's fine.
Alright. 3,
Just take a
2,
picture with it.
1. Oh, alright, come in. Alright, 3, 2, 1. And you have the meta logo on your face.
Yes. Then thank you everyone for coming. Congratulations to all the authors. Maybe we can get one more picture with the speakers. Angela, you can come. Omanga, you can come.
Picture with speaker.
Our speakers have run out.
They're not here. We have to.
Don't we have one more?
Yeah,
that's why
they're
not here.
That's why they're not here. I will find them.
Yeah.
Thank you. So.
We'll stand here.
I need something to take out.
Oh, you stand behind.
I should go there.
Right.
We can ask someone to.
Yeah. I can take it.
Yeah. Yeah.
Right.
Thank you. You can also take a picture as well.
Oh, yeah.
Very, very intense.
Very, very.
Yeah. Well planned. Oh, yeah, we talked over email, yeah. Nice to see you. I didn't know you were coming. Good to.
Okay, I should catch it.
Yeah, no problem. Yeah, happy to help out, Bill.
Nice to talk to you a lot more.
For sure. Yeah, thank you.
Is the paper or is the papers out there, but the presentation is it something that's
It's a one slide, so maybe I could share like a PDF with you.
If it's.
Yeah, I can, the papers are all out. Yeah, I was saying.
Yeah, I'm gonna be here.
Work copy on. I don't know.
Like-
Oh, I see.
Going beyond.
You were.
Might not work.